as we see, a lot of applications are gaining traction towards using AI, simple to complex models, right? So what is the state today? So can we trust those models? Can those for example, if you are using AI models in a safety critical applications, can we trust them? So that's the question many people are asking today, right? So how do we trust a model? So we can trust a model if we are able to decipher the decisions made by the model. So that means we should be able to explain the decisions made by the model, right? So how a model is able to make a decision. So what is the reason behind that? What is the formal specification behind that? Right. So let us look into these aspects briefly today. So this is the outline of my talk. I will give you a brief introduction about the theme of the talk. Then I will talk about the landscape of trustworthy AI. So majorly focusing on four pillars. The first one is robustness and adaptability, introspection and explainability. So I will talk about these topics briefly. Then I will focus more on to the first one, which is robustness. In that, I will talk about what are the various kinds of attacks can happen on AI models and what are the methods to generate attacks and what are the methods to counter the attacks. Then how do we evaluate the robustness of a model? So if I have to say a model is robust, how do you evaluate? Like how robust it is? There should be a metric. Then I will showcase some of the case studies. After that, I will make concluding remarks. Right. So artificial intelligence is in a crisis. Probably I'm too negative here, but there are some issues. For example, if you are using an artificial intelligence model, a complex model in any of the safety critical applications, even if you take an application related to health or cyber security, right? So we cannot really trust it completely unless and until the model is robust and explainable. So otherwise, we really don't know how that model is able to make those decisions. What is the criteria to make those decisions? So that's the reason today, when before we use any AI model, so we have to ask questions. Can I explain the results of the model? Can I explain the decisions made by the model? So can the model generalize well? So these are the questions. If we can't answer these questions, so then we can say that yes, using AI is kind of, we are in a crisis. So let us look at a simple survey. Normally, we feel Germans are normally in favor of automation. This is the survey made a couple of years back about the trustworthiness of AI models. The first one is I would trust a fully autonomous vehicle. So 41% of the people says yes, they can trust. I would trust a fully automatic technique to manage my finances. Only 16% says yes, they can trust an AI model. I would trust a medical diagnosis that is made without a human involved. Only 7% says they can trust, especially in health. The trust score is very, very less. So that means something else. AI models requires some additional characteristics to make themselves trustworthy, right? So like human being, AI models also makes mistakes. So like we also make mistakes. So for example, road accidents is the biggest global killer of teenagers. So that is most of the times that happens because of human mistakes. So similarly, even AI models also can make mistakes, right? So how do we make them trustworthy? What are the major characteristics a model should have? The first one is robustness. It has to, a model should be robust towards unexpected or adversarial conditions. Second one is introspection. It should be aware of its own performance as well as failures. Third one is adaptivity. So it should adapt to the new situations or goals. And the fourth one is majorly explainability. So we should be able to explain the decision made by a model. So if you're able to explain them, explain the decision, automatically it will be transparent and fair. Right. So overall, what I would like to say here is a learning system should behave like a human. So if it behaves like a human, so automatically we start trusting AI models. Right. So why our AI systems are not trustworthy? So let me make a simple comparison of a machine learning algorithm development and a traditional software development. So normally for a traditional software development case, we will have a formal specification. Okay, so whereas for machine learning, we normally they rely on exemplary data. So let me show details further. So in the case of a simple, in the case of a regular software development process, we follow these steps. One is, first thing is we define a formal specification. So that means the output, what is the output I'm expecting for a given input, right? And then if I know the specifications, then I'll start writing the code, probably a subroutine F. It will take the output, sorry, input, and it will give an output, right? So third step, how do I make sure that the subroutine developed by me is working as expected? So we go for testing. Then we do formal analysis or verification, so we can mathematically prove that yes, this subroutine is actually requiring capturing all my specifications and is able to behave as expected. But whereas in the case of a machine learning model development, we follow a slightly a different approach. Let me take an example of sentiment analysis. I am giving you two examples here, right? So the first one is this short movie is the best. It is a positive or a negative review comment, so it's a positive review comment, right? Similarly, I have another review, positive review comment, which one is the best thing about this movie is how short it is. In fact, the second reviewer has twisted that sentence slightly in a different way. So now a human being will be able to differentiate between these two sentences. Whereas if you give the same two sentences to an AI model, it may not be able to do it may not be able to differentiate between these two. So that is the complexity AI models are facing today. Right. So how do we build what is the method, like steps we follow to build a machine learning model? So first one, probably we install a library. Here we have to build a system for sentiment analysis. Probably we need NLTK library. So then we create a data set. The data set will be created by asking several reviewers to review the movie or anything, and collect those reviews and keep it aside as a training data. Then we know the target outputs. The reviewer has to sit, some expert has to sit and label them manually, right? So then we run the library's training routine, right? So same F. So it takes a review and it has to give me an output either positive or negative. So that's what the sentiment and classification is. So here, how do we test? So this is where this is the place where the major difference comes between the traditional regular software development and an ML model development here. So how can we test it? Probably we can test here, collect more reviews and ask the expert to label them and pass those reviews to the model, get the output and compare with the original labels, right? So that's how we do. Can we verify it? May not be. So we don't have any formal specification for AI to verify it. So whereas in the case of software development, we can develop theory and we can verify it. Here, we don't have formal theory to verify it. So can we analyze it? May not be. Not always. Sometimes if you use a simple model, you may be able to analyze. If you use a complex model, you may not be able to analyze. So this is what is the crisis what we are facing in AI. So though there is a lot of work is happening from the last 3-4 years, but still it is not emerged completely. So to summarize, this is the landscape of trustworthy AI. So an AI model, to call it as trustworthy, so it should have these four major characteristics. The first one is robustness, introspection, adaptivity, and explainability. Right. So let us see the solutions for all these four. So can we make a model trustworthy? Right. So what are the, we will look at the problems first, then we will look at the solutions one by one. So let me focus on the first characteristic, which is robustness. So the robustness means an AI model should react well to unexpected or an adverse cell condition. So how do we say that it reacts well? If you look at the typical statistical learning theory, you take any model F here. So F is trained on X, a set of inputs. Then I am computing loss or error L. Then E is here is expected error on future data. So that means on test data, so this is my expected error. So normally if you ask any person, right, so what he will say that is on test data, it should give less error, or it should be more accurate when compared to the training data. So though normally we in a regular, like in NML, it is reverse. Normally we get less accuracy on test data and we get more accuracy on trained data. But what we expect is normally, so we are very greedy. So what we expect is once we deploy the model, it should perform very well. So that's what is the expectation, right? So in real life, these assumptions are often violated. So because of a lot of adversaries which comes into picture when we expose our model to new data. Right. So let me show you some examples here. The adversary can come at the time of data collection itself. So when we are collecting the data for face recognition, so let us look at the first picture here, right? So we may not capture the images uniformly. Maybe some images, some faces must be facing the camera and some may not be facing the camera. Some may be having a different posture, a sitting posture. Some may be having different sitting, altogether different sitting posture here. So here the bias comes from the data collection itself. So another example here, the labeling bias. So if I have given you an image of an image here, it may be a truck or it may be a lorry. So the expert, whoever is labeling it, annotating it, so he may give a label truck or he may give a label lorry. So there is a bias in annotation as well. And the third one is static world bias. So here there are a lot of objects which are similar to each other. For example, if you see here, it may look like a pencil sharpener, or it may look like a fidget spinner, it may look like a hard disk, right? It is very difficult to label them. So this bias comes because of the similarity of the objects in your data set. Okay. So the another set of adversaries, how they can come. They may come because of some noise. Okay, so if you look at the example one here, this is a natural image of zebra. So example two, right? So that is also an image of zebra. But if you give both images to model, for the first image, it has classified correctly and it says it is zebra. But for the second image, it has classified it as toaster. So now I got a surprise. If I look at with the naked eye, they look both the both look similar here. So, but if you look at the difference, so I try to find out what is the difference between these two and why my model has failed. So if I look at the difference, if you look at the difference with naked eye, it's a blank screen. That means it looks like there is no difference. But if you magnify it and see with the 20x zoom, if you magnify it and see, there is some noise in example 2. So that's the reason for example 2, my model has failed here. So that is, we normally call it as an adversary. Right. So the second one is introspection. So why a model may fail to introspect itself? So what is the problem? What is the meaning of introspection here is to repeat. So the model has to know, right, what it can do and what it cannot do. So where it can be successful, where it will fail, right? So why it will not be able to do, I'll tell you. So look at the first image. I am giving in a picture of skiing, right? So this my model is able to predict well. Second picture, I might have rotated a bit. My model has failed. Still, there is not a problem. Probably I can retrain my model with rotated images. Then it may give good accuracy. That's not a problem. It can be solved easily. But looking at the third one, I just gave a blank image with all pixels with black color. So my model is telling that it is a website. Look at the fourth one. I just gave random noise to my model and asked it to classify. So it is classifying it as a tennis ball. So why it is happening? Because my model got trained with three objects majorly. One is sky, maybe one is website, the other one is tennis ball, right? So if you give the fourth category, maybe that is something else, right? It doesn't know that there is a fourth category exists because it has limited knowledge. What is that knowledge? It knows only the features of only three objects, three kinds of objects. That means there are only three classes. You give any other object, right? It will try to give a class which belong to these three classes only, predefined three classes on which the model got trained. So that is a problem. So here, if I have to say in a simple language, the model is unable to say, I don't know. Instead, it will try to classify, it will try to give a class, which, whatever the class it knows, whatever the classes it got trained, it will try to one of those classes to the new objects. That means it is unable to introspect itself. That is the second problem. The third one is adaptivity. So most of the times, the models are unable to adapt to the new situations. right? So how? Because the new situations, when it is encountering a new situation that may look similar. For example, here it is this is a fit spinner, but it may look like a pencil sharpener, right? So it is unable to differentiate between this new object and the old object. It is unable to adapt to a new situation here, right? So the fourth one is explainability or transparency or fairness. So let me give you a scenario. So a postdoc applied for a job and it gets rejected by a human being. So she is asking me why. So my answer is because you do not have enough high quality publications. So that is a very clear explanation and she will be convinced. So let me take a scenario two where the decision is made by a neural network. Here, the neural network has rejected her application and she is asking why. So what neural network can say that? So neural network might be saying, my output, whatever I got is a negative number, that's why I have rejected you. If I get a positive number, I will accept your application. So here we all know that neural networks or anything, right? This algorithms works on numbers, right? So your neural network is not really able to explain why the application is getting rejected here. So is it true always? Maybe if you use simple models like Navier-Bayes, decision tree and all, you will be able to explain. It is easy to explain, but the problem is they may not be accurate. If I use complex models, right, they are very accurate, but the problem is they may not be able to explain their decisions. So it's like a catch for us. So whether to use a simple model and explain the decision by compromising in the accuracy, or use a complex model where you get good accuracy, but I will not be able to explain the decisions made by the model. So we have to take a decision here. And let me talk about fairness. Right. So a postdoc applies same examples, right? So she's asking same things. So is that because I'm a woman, you are rejecting me? Right? So, but human says no. Uh, I have not rejected your application because you're a woman. So I have rejected your application because you do not have enough high quality publications. If the same question it asks to a neural network, so what it says, a model can say, it may say, maybe, we really don't know because it can't explain that. So here, she's not really sure about whether the decision made by neural network is fair and unbiased, right? So practically, I just tried a very simple example here on Google Translator, right? So since for Hindi, English to Hindi, it is doing very well. So I thought, let me take some language where there is a less corpus, where it can fail. So I took English to Turkish. Since I don't know Turkish, so what I have done is first I have taken English sentences and then translated Turkish. Then from Turkish I have from then English to Turkish I have done. Sorry, Turkish to English I have done. Okay. So if you look at this, my first box and the last box should be same if the translation is not biased. Right. So, but if you look at this very carefully, the original text is she is smart. But what is my translation happened at the end? When I do English to Turkish and Turkish to English, he is smart. So my translator is changing the gender. So look at the last sentence. It is very significant. So original sentence is he is a nurse, but the translated one is she is a nurse, right? So what might have happened here? So the model might have trained with a set of sentences or a corpus where, right? So most of the 90% of the nurses may be of female category. So that's the reason whenever the nurse is coming here, probably it is assigning a gender here, she. So here we can clearly say that my model is very much biased towards gender, right? So these are some problems. So how do we encounter them? So how do we solve them? So first, let us see the solutions for three. Robustness, I'm slightly shifting towards the end so that we will have more details on that because that is the most important pillar out of four. I will explain only the three things first. So let me talk about introspection. So can we introspect our model? So I instead of going in too much math, I try to give some of the simple solutions which are published. So can we introspect my model? So one solution is simple statistical two sample test. So that is also called as KS test, Kolmogorov-Smirnov statistic. So what exactly it will try to do is, right? So the red color line, look at the graph here. The red color line, sorry, I'm really sorry. The x axis here is the data, x, and whereas y-axis represents the output in terms of probability. So the red color line here is the it is something like predictions, original predictions, okay, on the trained data, whereas the blue color one are the probabilities or predictions made on test data, okay, so are unknown data where my model has failed, right? So if your model is able to introspect well, the gap between these two should be less. So if your model is unable to introspect, then the gap between red and blue color line is something, it will be big. So that's how we can make out your model is really able to introspect or it is unable to introspect. So this is one of the tests we can do and check. Right, so in the interest of time, I'm skipping these two. The second one is adaptivity to new situations. Okay, so for example, my model has trained on class 1 and class 3. Then all of a sudden a class 2 object has come. So how my model will be able to adopt this third class? So there are some approaches here because the model has most of the models has one drawback here. So what is the drawback is if your data has hundreds of classes, if you train your model with all 100 classes at a time, there is a problem of catastrophic forgetting. Your model may forget whichever it has trained. For example, first class of objects you have trained, then second class, third class. The moment it reaches 100th class, it might have forgot the features of the first class because it has seen those features long back, right? So that is one problem, right? So what is the solution here? How it will be able to adopt here, right? So one solution probably you can go with incremental classifier or representation learning. So in incremental classifier, what we try to do is we try to train your model with a fixed size deep network first and regular backpropagation method. Then what we do is in the second step, we take a small set of exemplars from all classes seen so far. So earlier I have done incremental, that means one after the other. Then in the second iteration, what I will do, it might have forgot, right? Because as I mentioned, because it has seen the first set of samples in the beginning, way long back, it might have forgot the features of that. So I will try to remember or remind it. So I will take another small set of exemplars or samples from all the 10 classes or 100 classes. Again, I will try to retrain it so that it will remember, oh, so these are the samples already I have got trained long back, right? So it will try to remember. So that is one solution normally people adopt. So the third one is transparency or explainability. So let me give the same example of sentiment analysis here. Take two reviews here, right? So I would like to tell you whether it is transparent or explainable or fair or not. So here, take a simple review. This book is awesome. So the whole focus is on the word awesome. So that is a positive word. I am assigning a score +1 so that the review is a positive review. A second review is I hate this terrible movie. So here hate and terrible are negative words. So I am giving negative scores of -1 so that my final review is a negative review. So here I am able to explain why it is a negative review and why it is a positive review. So let me take this. So let me take another critical example here. So this knife is really sharp. So here the word sharp is a positive word because a knife should be sharp to right. So it should be a positive thing. But whereas in the second sentence, the crib had sharp edges. Here it is slightly a negative thing. It should be a negative. But what happens if I give positive score to sharp? I have to give the same score in the second sentence also. If I give +1 here, I have to give +1 in the second sentence also. That means your model will be able to classify either first sentence or second sentence correctly, right? So and here it is very difficult to explain because there are contradicting decisions here. So a single word score model may not be able to solve this problem or reflect both. So what is some solution is learn several models and based on the context switch between them. So that's where the ensemble models have come into picture, right? So we have seen three characteristics. Now I would like to go towards the most important characteristics, which is called as robustness. Okay. So What is robustness, or what exactly is the problem? So earlier, attackers normally used to focus on the code, but nowadays what has happened is most of the applications rely on data. So that means if you are able to corrupt the data, so your goal is achieved. That means you are able to make the safety critical system malfunction. So the focus has shifted towards data, right? So my model has to be robust to these kind of adversaries. Okay. So what is exactly is robustness called as? So if I have to say a model robust, it should be safe and secure, not vulnerable to tampering or compromising the data on which they are trained on. So what exactly is an adversarial attack? You take a simple image here, a fish, right? So then if you feed this image to a trained neural network, it is able to classify it well with the 0.9 probability. But what I have done here is I have introduced a small adversary or a noise here, which is a very, very small noise here. I didn't even change the shape of the fish. Nothing has been changed. Only thing is I have overlaid some noise on top of this fish image. You look at this, what is the result of my model? So here, instead of classifying it as a fish, it has classified it as a cat with a probability of 0.9. So that is what is the impact of adversarial attack. So let me show you a couple of more examples quickly. So here I would like to recognize a desert by a neural network. So if you take the first legitimate input and feed it to the neural network, it is able to classify it as 1. But what I have done here is this input size is of size 32 by 32 pixels. That means it has 1024 pixels. So out of 1024 pixels, I would like to change only 8 pixels. You look at the second image here, adversarial image. Here only 8 pixels I have changed. Earlier originally they are in the black color. I have made them white color. Now I have passed this image to my neural network and asked it to predict. Now it has predicted it as 4 as expected. We can expect it's looking like 4. So, but how I made, what is my adversary here? Only 8 out of 1024 pixels have been changed. The class of this image got changed easily. So these are the kinds of attacks are called as adversarial attacks. Similarly, we have lot of examples here. We can have a kind of a mosquito net um, noise which can be overlaid into image, and we also impact. Also, we also um, um, introduce noise into audio files also. So for example, you just look at these two audio files, listen to these audio files. This one is normal. I'm just repeating. So it is without the data set, the article is useless. So look at the adversarial waveform. You can see some background noise here. You can listen some background noise here. So this is original. I'll just repeat. Quite clean. So here I have purposefully added some noise. So if I give these two waveforms like audio waves to my model, so the first one it is able to give me the text, speech to text very nicely. Without the dataset, the article is useless. In the second one, I have introduced some 1% of noise here. So it says altogether it gave me very interesting sentence. Okay, Google, browse to evil.com. Right? Altogether, the translation has been failed. Right? So similar thing can happen even in the case of image segmentation also. You can see here there are human being here. If I just introduce noise here, probably my model may not be able to detect human being on the road, right? So there are a lot of examples. So let us look at what are the various kinds of taxonomy of attacks, right? So there are majorly we can classify the attacks into 5 categories. The first one is timing based. The second one is goal based. The third one frequency based. Fourth one knowledge based. Fifth one falsification based. So I will just go through of each of these things. In the case of timing based, the first one is poisoning attack. So what exactly it will do here is the timing based attack means the attack can happen at the time of training, or attack can happen at the time of inference or prediction. So the poisoning attack happens at the time of training. So what it means is it is a white box attack. That means the attacker has access to the data as well as the model, input data, train data as well as the model. So what he will do is he will try to inject some bad data or bad noise into your model's training pool. So that is called as poisoning attack. The second one is evasion attack. So here the user don't have access to the training data, but so he has access to the application API where the model is deployed. So whenever you are trying to make an inference on a particular image, that image he can access. So he will try to introduce noise into the new image on which you have to predict. So then my prediction can go wrong. So this is happening at the time of um, inference. So this is called as evasion attack. So these two are based on timing based attacks. The next one is goal based attacks. So the goal based attacks means they focus on a certain class. Okay, for example, I have a face recognition system, right? So he would like to disguise a face as an authorized user. So that means he is focusing on a particular use. For example, a bank manager wants to log in using face biometric. So then he will make sure introduce some noise. Whatever the face comes, it will recognize as a bank manager only. So it's a kind of a targeted attack, targeting on a particular class. So non-targeted attack, he's not worried about which class he wants to change, positive to negative or negative to positive. He's not worried. Only his goal is the model has to misclassify. So there is no specific target on a particular class. We just want to make the model misclassify for all kinds of classes. So that is called as non-targeted attack. So other third category is frequency based. Some kinds of attacks are normally can be introduced with a single iteration, that is called as one time. I have a slide on that. So some attacks maybe require many number of iterations. So normally iterative attacks are more robust, right? So the fourth category is falsification. So this is very simple. So what he will try to do is the false positives, he will try to make it as classify it as sorry, the negative samples he will try to make it as positive samples here. Second one is false negatives. So the positive samples he will try to make it as a negative sample. So the positive samples will be classified as negative sample will be classified as positive sample. So this is falsification attacks. The last one is an umbrella kind of thing. So based on the knowledge what he has, it's a similar to our cyber security classification. So first one is black box attacks, and the second one is white box attacks. So in the case of black box attacks, he don't have access to data. He don't have access to the model parameters, weights and biases, and he don't have access to the model architecture here. So what he has access, he has only model. So only he has to do some only black box attacks. I'll show you an example after that. Okay. So the second one is white box attack. Here he has all kinds of information. He has the data, access to the data. He has access to the architecture of the model. He has access to the parameters of the model, right? So, so what are various methods? Since in the interest of times, I'll show you a couple of methods like how to generate attacks here. So there are good tools that are available. You can experiment. I can classify into two categories here: white box attacks and black box attacks. So in white box attacks, I have two classes again. The first one is gradient based attacks. You can see here DL by DX. What exactly he will try to do here is whenever there is a model is uh, getting trained, right? So it is a white box attack. So that means he can include at the time of he has the data input data, access to input data also. He has the data access to all other things. So what he will try to do is the model gradients, he knows how they are going to change, because the gradients are the things which are in fact are fine tuned to get optimal weights and parameters through backpropagation. What he will try to do is he will try to divert the gradients in a very fast manner towards in a wrong track where the accuracy falls down. So normally what happens is any of the optimization algorithm tries to optimize the track of these gradients so that the error will be minimized, so that we will get optimal parameters, weights and biases. But what he will try to do is he will try to change the track of the gradient so very fastly, so that it will go out of the track. In turn, it will not be able to find out the optimal weights and biases. In turn, my model accuracy will be very less. It's not efficient. So this can be done. The change of the gradients can be done in a single step, or it can be done in iteratively also. So originally, long back in 14, 15, people used to use a single step attacks, but later on, people found a lot of attacks which uses iterative optimization methods. So that is about white box attacks. So in black box attacks, we have two kinds again, decision boundary approximation. So here, what is the meaning of decision boundary? Decision boundary means, if I give you an example of SVM, the hyperplane is a decision boundary. So what he will try to do, decision boundary approximation, he will try to simulate a model which is similar to the original model, because he don't have access to the architecture, parameters, everything. He has the access to only the model. So here he will create some synthetic data and try to probe, try to infer, make the predictions using the model on which he got access. Then he will try to observe the behavior of the model here and try to generate a decision boundary, approximate decision boundary, so that he will get to know the gradients here also, but approximately. Okay, so that is one thing. So the second thing is heuristic search. It's a brute force method based, like people normally don't use. It is very exhaustive. I don't want to focus on that. Right. So let me give one simple white box attack. People have defined a new network which is called a spatially transformed network. So when I say white box attack, means they have access to data. What exactly he will do is, they will take a normal sample, which I classified as benign here. Originally is probably it is a normal sample. So what he will try to do is, he will use some spatially transformed network. What is the meaning of spatial transform here is, instead of directly modifying the pixel values of an image, he will try to modify the location of those pixels, so that if he just shift these pixels towards right side, right? So you may be able to see in the third image, if you see very carefully, it may look like some 50% or 70% portion of the digit 2. Originally, it may be digit 1, but the third picture is looking like some partial digit 2. So that's how they will try to impute using spatially transformed networks. So it is one of the white box attacks which are famous and published in 2018. Right. So second, I want to give an example of black box attack here. Here they try to approximate the decision boundary. Already I have told you. So this is one of the interesting technique which is called a substitute black box attacks. What exactly they will try to do is, they have access to the model. Then they try to train a substitute model or a kind of a simulated model on synthetic data set. So the data set, he knows, like he might be having information about on what kind of data this model got trained, right? So they try to generate similar kind of synthetic data set and try to generate a substitute model, right? So that's, I can call it as black box model. So right. So this is one thing which we call it as substitute black box attack, right? So we have seen a couple of attacks. Now let us look at some of the defense methods. So they are majorly categorized into two categories. One is reactive. So that means detecting the adversarial examples after deep neural network are built. So this happens after training. So some ones are proactive. So make my deep neural network more robust. Why I have to wait for the attack has to happen, right? Why I have to wait for the till the training phase is over. So these are two kinds of attacks. We will see some of examples. So in the reactive is something like which happens, which is kind of input reconstruction. Whenever there is an adversarial example comes into picture, right? Whenever I want to make an inference here, every every image on which I want to make an inference or make prediction, it can go through a denoising autoencoder. So here autoencoder can denoising autoencoder, what it will do is it will try to remove the noise, so that the image may be whatever the adversary which is added in the form of noise can be removed by denoising autoencoder. So this is one of the methods for input reconstruction based defense, right? Second one is proactive, which is network distillation. I will explain what is the meaning of this is. So what we do here is, I take a training data here. I am talking about the original network. So I take my training data X here. Then I have a set of labels for that. Then I will take a deep neural network and train it. Then Here, what I will do is every deep neural network, especially in the case of classification, it will give you output probabilities of every class also. And at the same time, it will give you the labels, predicted labels also. So I will have two kinds of outputs. One is the probabilities of predictions of all the classes and the predicted labels also. So I will take the probabilities of the predictions, then that I will take it as that is something which gives a lot of knowledge to us normally. So earlier also I was telling in one case, you have to, if you really want to see whether a particular model is robust or not, right? The probabilities will tell you very clearly. So let me give a simple example. I gave a cat image to a neural network. It has predicted as a cat with a probability of 0.6. So 0.6 is greater than 0.5, still it will classify it as a cat. And another neural network 2, which might have predicted it as a cat with a probability of 0.9. So model 1 0.6 probability, same class, prediction is same. Model 2 0.9 probability, prediction is same, but the model 2 is more robust because it has predicted with higher confidence level. Right. So that means the probabilities instead of the predictions, the probabilities gives me more knowledge and more information. So what I will do in network distillation is take those probabilities, class probabilities knowledge, and take a distilled network. Normally a small network we call it as. Okay, so the original network is called as a teacher. The small or distilled network is called as a student. Okay, so the probability distributions what I got from the final layer, that will be taken as a labels here. For the small network, student network or distilled network, training data is same. So with the training data and the predictions made by the bigger network, the probabilities made by the bigger network as the labels, I will train my student network. Then now I will get a probability vector predictions here, final probability vector predictions here. So this method gives me more robust model when compared to only the original network which I am showing in the first box. So this is one of the proven technique which is called as network distillation for defense, right? So the other thing is adversarial retraining. So adversarial retraining is a very common method. So in which what we do is I have, for example, the images of 100 cats, okay, and 100 dogs. I want to train a network. Now what I will try to do is purposefully for every image here, I will introduce some noise, maybe a Gaussian noise or something, pepper noise. I will introduce some noise, right? And that means for all the 100 cat images, I will introduce noise. That means I will get 100 more new images with noise. That means the cat class has 200 images now, 100 original, 100 adversarial. So similarly, dog will have 100 original, 100 adversarial. So now I will train my model with both original as well as adversarial. So here the what is the trick here is for original cat image as well as for the noisy cat image, the class name is same. So that means my model will come to know that yes, even though there is a noise in this cat image, this is also cat only. The label is cat only, right? So that means you're training your model with adversaries. It knows it is an adversary, but it belongs to cat only. So that is what is called as adversarial retraining. So these are some methods for defense, simple methods, right? The last part is how do we evaluate the robustness? Um, so most of the times what happens is we focus on misclassification ratio, but where this misclassification ratio can fail. So misclassification ratio alone may not be sufficient because what can happen is, for example, I have a model which is built for cancer prediction or tumor prediction, let us say tumor prediction. So in my data set, there are 99 people are normal subjects, healthy subjects, only one has tumor. So my model is able to predict all 99 correctly. Only for one it has failed. That one is the person who has tumor. Still, I can say that classification ratio is 0.9. That means 99% accurate. But it's like operation success, but patient died, right? So what is happening here? 99% is the accuracy, but what has happened? What is my target? My model should actually focus on the patients who is having tumor. So where it has failed. So misclassification ratio alone is not sufficient to say that whether my model is robust or not. So we have a lot of other metrics here. For example, perturbation sensitivity distance. If I add perturbation to my input images, right? So what is the distance between the original probability, original output probability of my network and the probability distribution which is created, output probability distribution which is created using the predictions of noisy or perturbed samples, right? So the distance I have shown even in the case of KS sampling, right? And noise tolerance estimation, robustness to Gaussian blur. There are many techniques, evaluation metrics which are present, and instead of using one, we may have to use a lot of metrics to evaluate a particular model to say whether it is robust or not. Okay, so finally, let me show a couple of case studies very quickly. So what we have tried for a experimental purpose, we have taken histopathology cancer detection, and we have tried to impose some attacks and defenses here. It is of size 6 dB data, and each image is of 32 by 32, and it has positive and negative. So I have used gradient sign attack, which is white box attack, and defense I have used adversarial retraining. So if you see here, this is my original image, the first one. The second one is after I apply the fast gradient attack. Then what is the impact? Accuracy of my model before attack is 75%, whereas after attack it has drastically came down to 35. And I have once I included defense model here using adversarial retraining, so it has gone up to 77. If you see very carefully, my after defense, the accuracy is more than the accuracy of original model. Right. So second one is we tried on intuitive detection system dataset, so open dataset. So here we have used a very interesting attack here, Jernicke movements based attack. So what we try to do is we try to convert my data into a series, a Jernicke series. Okay, so with 36 components in it. Then what we tried is Jernicke movements is a kind of a series, spectral series, like Fourier series. So what we tried to do is slightly altered out of 36, slightly altered only 5 terms, sorry, 6 terms, 6 out of 36, 16%. Okay, then what has happened? So then you can see the results here. I have applied some 5 attacks here, and we can see accuracy before defense 56%, 43, 51, 31, and 34. Then I have applied here network distillation defense method. So you can see the 56 has increased to 78, 43 has increased to 65. So we can see the impact of defense as well as attack as well as defense here also. The last one is quite interesting. So can we apply attacks on videos also? Okay. So we have taken a kind of a very small clip of 30, sorry, I think some 60 frames in that. So I have to generate a caption here. Okay, so the original caption is you have beautiful eyes. You see here the focal point is eye here. So how do I generate attack here? So we have used a technique here. For every frame, I have taken every frame here. So wherever eye is there, so there I have introduced more noise. More noise here. Even other frames, other tiles, right? Other tiles, there also I have introduced noise, but with less intensity. So that's what we have done, because here focal point is high here. So after attack, what has happened? If you see, this is what is after attack. You are so angry. So here, this is the original. You have beautiful eyes. After attack, so what I got is you are so angry. So this is what is the impact of lack of robustness of models. So what we are supposed to do here, AI is a protector. That means even in cybersecurity, for most of the problems, we are relying on AI models. So that means AI is a protector here, but AI model itself is going into the mode of attacks here. So how we have to protect? So we have to protect the protector. So there are a lot of tips. Some tips here, focus on the strongest attack possible when you're building a model. Simulate the strongest attack possible and see how robust your model is before deploying it. Second, do not only use attacks during testing that were used during training. So try to use different attacks at training and different attacks at testing and see how your model is responding. Third one is don't apply nearly same identical attacks. That may not be useful to you. So that's a well known. Fourth one is properly ensemble or randomness. Sometimes even randomness creates this clumsiness and affects robustness. So you have to fix the randomness to have a reproducibility. Fifth one is verify attack convergence. See what kind of umbrella of attacks you are using for a particular problem, because the attacks are problem specific sometimes, though I didn't explain in that way. Carefully investigate attack hyperparameters. What is the meaning of this is, so I may think I have applied Gaussian noise and I have evaluated, but what is the intensity there? Gaussian noise with 0.2, 0.3 intensity, or 0.4, or 0.5, or 0.9. So when you are simulating attack also, you should be very careful what kind of hyperparameters you are choosing there. Okay. So last one is try some brute force search attacks and see how your model is responding. So these are some simulations you have to do on your AI models before really deploying them into safety critical applications. So in summary, artificial intelligence has great potential in cybersecurity, in safety critical applications. But the problem here is people do not trust AI for important tasks because of four characteristics. If it doesn't have these four characteristics, robustness, introspection, adaptivity, and explainability, so then we cannot really trust that particular model. So we should make sure that every model, whatever we are deploying in a safety critical application, should have these four characteristics within built into it. So this is an emerging area, so a lot of open research questions. That's all from my side. So thank you so much. I'm open to questions.
Thank you so much, sir, for your enlightening talk towards robust AI and speaking about different attacks with examples and giving some countermeasures, and also speaking about some case studies. And in these vulnerable days, the information you have provided with us will give indeed a valuable information, sir. Once again, thank you, sir. And as of now, we don't have any questions in the chat box. So participants, if you had any questions, you can post it in the chat box. Sir will answer you.
Sir, you are on mute.
Thank you, Ramesh.
Thank you, sir. Thank you so much.
It's a wonderful talk, and I just wanted a small this thing. You talked more about explainable AI, right?
Right, sir.
So there is another word also, responsible AI. Can you throw some light on that?
Here, actually, these words are kind of correlated. We say in terms of AI, so they are very correlated. Though we coined a lot of terms here. When I say responsible, what is the meaning of that? Is it has a different meaning in different context. So, as per my knowledge, so I have used one application in health. I want to see what is the impact of addiction like alcohol or anything on your brain regions. So there, I should not deploy a model without really interpreting the model very clearly. So, uh, so before deploying that model into a hospital, so I have to really interpret. For example, it has thrown that, yeah, these are the six regions, brain regions, which are getting affected because of alcohol addiction, right? So that six, how do I interpret that? So there, I have to go into formal methods, formal verification, and formal methods. There are formal methods, like there are libraries also like SHAP and LIME. So I formally verify and make sure that I am not really making any responsible decisions by deploying that model. So that's what I can understand in that angle.
Yeah, it sounds good.
Yeah.
Thank you.
Thank you, sir.
Yeah, once again, thank you so much, sir, for inviting for accepting our invitation and giving a wonderful talk. And as we are running out of time, we will go with the next speaker, sir. Once again, thank you, sir.
Yeah, so thank you very much, sir, for inviting and giving me an opportunity to present this. Thank you so much, sir. I'm signing off.
Yeah, looking forward.
Thank you, sir.
For more contributions in future.
Yeah, let me introduce our next speaker, Mr. Swati Mitran. Mr. Swati Mitran is working as a scientist in cryptology and computing research group, SETS. He has completed his ME in computer networks from Pune University. He was previously working with Applied AI group in CDAC, Pune. He has 6 years of experience in deep learning. Currently, he is working on projects related to ransomware analysis, misinformation detection using deep learning techniques. And may I now request Mr. Swati Mitran to take over the talk.
Thank you, Nalini. Good afternoon, everyone. Am I audible?
Yes, sir.
Hello? Yeah.
Yes,
Okay,
sir.
thank you. Okay. Let me share my slides. Is my slides visible?
Yes, sir. Slides also visible. You can.
Okay. Is the slideshow visible?
No, sir. Actually,
Yes.
slides.
Yes,
Yeah.
Mithun.
Yes. It is moving. Slides are moving.
Going right. Okay. Thank you. Good afternoon, everyone. So the topic for this session is deep learning based dynamic analysis for malware detection. So in this session, we will be going through the basics of what is a malware, how and what are the costs or losses to the companies due to malware, and why we need to detect the malwares, and what are the different type of analysis which we can do to detect the malwares, and why we are going with the dynamic analysis, and why we are choosing a deep learning based dynamic analysis for malware detection. So let's move ahead. So what is a malware? So malware is nothing but a malicious software. It has some code which damages your system, or it is a kind of a script which runs to perform some malicious activity. So different malwares come in different formats. Like it can be executable, it can be a binary shell code script. It can be a firmware. Nowadays, fileless malwares are also there. So without any file, they will inject the code, and the code will be running it. So there will be no file in that. So it's a fileless kind of malwares are also present. So what are different types of malwares? So here we have ransomware. So the basic functionality of ransomware is it will encrypt, once it gets into your system, it will encrypt your data, or and all your data which is present in the system, and using a key, and it will demand a payment from you in bitcoins or cryptocurrencies. Once you give the payment, then you will be given a key to decrypt your data. The next type is a spyware. So spyware doesn't harm your system, but it will spy whatever activities you are doing. So it gathers the information about a person or a organization, and it sends this information into a other person to a entity whom they will be using it, right, to make harmful activities. So that's what spyware is. So what is an adware? So adware is just popping out the advertisements to the user. So from advertisements, they will be getting constant revenue from the advertisements. So for that, they will be infecting different systems in the network, and continuously they will open the pop-up and show the advertisements to the user. Then we have Trojans. So the Trojans are designed to damage and steal harmful actions on your data or a network. So, and worms. Worms are malicious codes that replicate itself without attaching itself to a software program in order to cause the damage. So once worms get into your system, it won't require any other software to attach it. It will replicate itself, and it will attack the system. So virus, it's in the same way virus alters the way a computer operates, and is designed to spread from one computer to another. It requires some host file. That's the difference between a virus and a worm. So virus requires some host to file to attach itself. After that only it will be able to propagate. But worms can propagate without any host file requirement. So what is the impact of malware? So these are some of the impact. If you see, 60% of the targets are manufacturing industries. So for manufacturing is the most targeted industry of the malware attacks. Similar to manufacturing, financial services are also attacked. Transportation, technology. If you see each and every sector which is using computers are or a which is using a technology, they get impacted because of this malwares. And on a financial account, if you see the ransoms which is paid per quarter, if you see here, if in 2011 itself, it's around 2 million dollars. And this is some of the estimate global ransomware damage costs. So by 2028 and 2026, it will reach around 71.5 billion of a billion of dollars with only a ransomware type of malware. And overall malware global cost will has already reached around 6 trillion and in 2021. So it becomes it becomes more important to detect malwares, and we need to detect them at an earlier stage so that it won't infect our systems, and there should be no loss with respect to the system or the financial views also. Malware analysis. For to detect a malware, we need to analyze the kind of what type of a malware is. So we need to analyze the behavior, its functionality, and and the impact of malware samples on the systems. Once we do the analysis, then only we will be able to get the function behavior, the features about the about the malware. So these are three different kind of analysis. First is a static analysis, the dynamic analysis, and memory analysis. So in static analysis, if we have some executable files, we won't be running those executable files. We will the files will be analyzed without running it. So there will be some binary codes which are present. So we using some tools like PEID, ARA, or IDA Pro, we will deassemble the executables. We will extract the information from that. So opcode information or the program itself from that. From that information and flow of the program and usage of different malicious usages of different opcodes, we will be able to find whether the malware is whether the executable is a malware or not. Coming to the next type of analysis is dynamic analysis. So in dynamic analysis, the malware code is executed in an isolated environment. So different tools which we use are Cuckoo, dtours, the fog server is also used for dynamic analysis. So once we run, we collect the logs from those dynamic analysis servers, and then we analyze those logs. Memory analysis is analogous, is related to dynamic analysis itself. So in memory analysis, what we do is we execute the malicious code, then find the memory consumption of the consumed by the malwares. So using those information or the patterns of the logs, we will be able to detect whether the malware, whether the executable is a malware or not. Similar to memory analysis, we have a network log analysis also. So different tools which are used for memory analysis are volatility, pin, Valgrind, etc. So static analysis. So analysis of source code without executing the application. So the executable which we have a portable executable. It has some file sections which we call it as a PE header, and it contains some of the information, important section informations. So the different informations which are present are .txt. This contains the executable code. So when you pack code or when you compile a code from your end, it converts into a executable. The executable contains a .txt file, and inside this .txt file, you have the code which you have written. Similarly, we have .r data. This section holds read-only globally accessible data. So we have some of the data which are globally accessible. So we need those data to be stored in a .r data. Dot data, this stores global data accessed through the program. So these are like different programs need to access those data. So for that, we store those information in the .data. .rsrc, this section stores resources needed by the executable. So if a program is needs a printer resource or some other kind of a resource, so those information are present in this .rce section. So that was all about the static analysis. So coming to the dynamic analysis. So dynamic analysis is a process of testing and evaluating a program while software is running. Also referred as it's also referred as dynamic code scanning. And dynamic analysis is extracting the API code. So when you run a program in a isolated environment, so whenever we do dynamic analysis, we run the executable in a isolated environment. So the system should not be connected to some to any other systems. So we run it and we try to extract the API calls made by the binary file in the execution. So when it is executing, we will get the logs of APIs. So whatever API, Windows API calls which it is making. So if it is a Windows platform, if it is a Linux platform, we will be getting the API calls from Linux platform. So why it is required? We need to get the information of what is the behavior of the malware file which is being executed. So different tools which are used are like I have already mentioned, Cuckoo Sandbox and D-tools are used for malware dynamic analysis. So using one of these analysis tool like Cuckoo, run and analyze the malware files and generate the analysis result of the behavior of the malware while in execution. The log file contains, yes.
Sorry, sir, for interrupting. So actually, audience are requesting you to go slow, little bit slow.
Sorry?
A little audience are requesting you to go slow, sir, little bit slow.
Okay, go slow. Okay, fine.
Thank you.
So using one of these dynamic analysis tool like Cuckoo, what I will do is I will install the Cuckoo tool in my in an isolated environment. And using this Cuckoo is nothing but it's a sandbox. So you have your sandbox installed. The sandbox will run the executable. So these malware files or the malware binaries, binary files are ran in the Cuckoo sandbox. So when you run it, you will get the API calls from it, and it generates an analysis result of how the malware is behaving while it is in execution. So this information is then used used to detect the pattern in which the API calls are being made. So the log file contains API calls made during execution, registry modifications, and the information such as heap memory address and process address. So APIs are provided by the operating system to access low-level hardware through system calls for application programs. So what it means is Windows or Linux platform, you have some API calls for having an access to low-level hardware. So whenever a program want to access low-level hardware, it will use the Windows API calls or Linux API calls. So these calls are provided by the operating system itself. So the attacker will use the same API calls. It will target these API calls, and to do some malicious activity, he will be using these API calls. The attackers use the same set of API to do malicious activities. Using the API calls, he will be doing some malicious activity. For example, uh, I need to get a list of all the directories in the present in the system. So he will be using the Windows API calls and he will get the directory listing. So using these different kind of APIs, he will be doing the malicious activity. So features. Similarity in the API call sequence between files in the same class must be greater than the similarity between the files in the different classes. So API call sequences between the files in the same class. So for example, you have some file, and in that file you have some classes, and the similarity between these API calls, if you see same class in the sense you have a malware of a same class, and the binary and the files which have So you will be having a similarity in the API call sequence. Hence, so these sequence should be greater than the similarity between the files in different classes. So we have different classes of files, and and the similarity between the files in different classes is will be different. So the conclusion is that in a same class, for example, if I take a malware of a Trojan, then the similarity of the API calls will be greater than, and the similarity between two files which are from different classes. So from this, we will be able to find the class of the malware which is being executed. So n-gram based method to analyze the call sequence using API call grams. So API calls can be converted into an n-gram based method. So what is an n-gram based method is, we have a if we have a 10 sets of API calls, then the sequence of API calls we can be in the form of an n-gram. So using those n-grams, then we will then what we will do is we will train our systems, train our deep learning model. So this is what is all about dynamic analysis and static analysis. So now why we need to go with the dynamic analysis, or what's the difference between static and dynamic analysis? Now using AI technique, AI is like a double thing. So AI is being used by the attackers also. So what they are doing is they are using AI to generate new viruses, so or new malwares. So AI generated malwares, they won't be able to get detected in static analysis. The code is obfuscated and we won't be able to unpack it, and it's difficult to get the information from the encrypted file. So what we do is we go with the dynamic analysis. Dynamic analysis is the proper way to get a proper way to detect the malware, because when a malware is running on a system, it will show its own behavior, whether it's malicious or not. It will be we will be able to know in and out of the of what the malicious code will be doing. So that's why we will be going with the dynamic analysis. There is a less success rate in the static analysis, and static analysis is more of a manual task. So that's the reason why we will be moving to the dynamic analysis. This is the basic difference between a static analysis and dynamic analysis. Some of these systems nowadays are coming with a hybrid approach where static as well as dynamic analysis are there. So both are good at their own thing, but in the future, more and more dynamic analysis will be used to detect malwares. Okay, so this was all about the malwares and how we are going to detect it. Now coming to the AI part of it. So what is artificial? This is just a basic thing. So AI is the ability of the machine to perform cognitive functions as humans do, like perceiving, learning, reasoning, and solving problems. The benchmark of AI is a human level concerning in teams of reasoning, speech, and vision. So this is just the basics. So this is a broad category of of artificial intelligence sectors, like in cognitive computing, in computer vision, and we have natural processing also. So these are some of the things. So why AI is now hype? It's because of the availability of hardware, data, and algorithm. It's not that AI was not there 50 years ago. AI was there since 1960s. But hardware was not there to do complex mathematical functions. We didn't have data, enormous amount of data. With a big data in picture, we have huge amount of data that is getting generated. Also, we have different algorithms and complex algorithms which to find different features which are present in the data. Machine learning steps. So some of these, this is the general machine learning step. Step one is the data collection. Then we prepare our data. Then we will choose our model. Then we train our model. Then we will have an evaluation. Then once the evaluation is there, we will be doing parameter tuning from those results. Then we will do the prediction. From where deep learning came? So from machine learning itself, we come to a deep learning. So if you see here, deep learning is a subset of machine learning, and machine learning is a subset of artificial intelligence. So machine learning overview. So machine learning has a two types. So one is a shallow learning, one is the deep learning. So in shallow learning, we have supervised shallow learning, we have unsupervised shallow learning, and in deep learning also we have the same divisions like supervised deep learning and unsupervised deep learning. So in shallow learning, we have the general machine learning algorithms. Those are naive Bayes, logistic regression, support vector SVM machines. We have HMMs, we have k nearest neighbors, and in unsupervised learning, we have clustering and association. Supervised deep learning. In supervised deep learning, we have a fully connected feed-forward neural networks. That's what we call as CNNs. We have convolutional for feed-forward deep neural networks. We have recurrent deep neural networks, that is called RNNs. In unsupervised deep learning, we have stacked autoencoders, deep belief networks, and we have deep belief networks. So introduction. Introduction to deep learning. So what is a deep learning? It's a part of machine learning field of learning representations of the data. These are exceptionally effective at learning patterns. It tries to minimize the difference between its prediction and expected output. And by doing so, it tries to learn the association patterns between given inputs and outputs. So why we need to go with the deep learning is because in machine learning process, we have a feature selection or a feature extraction process, and that process is a manual process in machine learning. So what happens is a person or we have to devise some of the techniques to extract the features from the image from the data set. So once that is done, then only you will be able to feed it to a model using some of the tools like some of the algorithms like naive Bayes or k nearest neighbors to predict or classify the data set. So this feature extraction process is a time consuming process, as well as it requires lots of hard work. To overcome this, we have a unsupervised shallow learning, but that too has its own limitations. So we won't be able it doesn't give much accurate results. In order to overcome these issues, deep learning is used. So in this, the feature selection is done by the system itself or the deep learning model itself. So it will these are exceptionally effective at learning patterns which are present. So we are not required to give a pattern to the learning pattern or a feature extracted to the model. So that's why deep learning gives more accurate results as compared to the normal ML or shallow learning. Types of deep learning. So we have convolutional neural networks, we have long short-term memories, recurrent neural networks, we have generative adversarial networks, so and some other networks also we have. So how these networks are designed? So we will be going through that. So this is just what is the inspiration behind deep learning. So these are human-inspired systems which replicate the way humans learn. Then, these are used in deep learning algorithms like CNN, RNN, GAN, etc. Each layer contains neurons called as nodes that perform various operations. So this node is a very important part of a deep learning thing. So the hidden layer. If you remove this hidden layer and if you connect input and output layer, then it becomes the normal machine learning. So this hidden layer is what is the difference between deep learning and shallow learning. And the format in which these hidden layers are connected with each other will give you a different type of networks, and the type of node which is being used in the hidden layers will give you will also be giving you a different type of networks. So deep learning uses artificial neural networks to perform sophisticated computations on large amounts of data. Neural network is structured layer of artificial neurons, which are also called as nodes. So these are called as nodes. So the structure of these artificial neurons and their network results in different forms of neural networks. Each form of neural network has its own applications. So what is a perceptron? So it's a single node which is used in the network. So we have a x1 and x2, we have weights w1 and w2, we have activation function, then we get a y. Y sigma is nothing but a multiplication, is a summation of x1, x1 and weight w1, x2 and weight w2. Then we will be adding some bias to that, and then we will be giving it to an activation function, and we will be getting the output y. So what is an activation function? So function that is added into artificial in order to help the network learn complex patterns in the data. So we need to learn complex patterns which are present in the data. Because there is no feature extraction part in the deep learning. So we use activation function to learn those complex patterns by itself in the data. It takes in output signal from previous cell and it converts it into some form that can be taken as an input to the next cell. So the output signal from a previous cell cannot be given as a direct input to the node which is present in the next layer. For that, we need to do some of the some function. So that function is nothing but the activation function. The most important feature in an activation function is the ability to add non-linearity into the neural network. What happens is if you don't have an activation function, the output will be linear to the input x. So we don't want that. We want non-linearity in the output and input. So for that, to achieve that, we use an activation function. So different types of activation functions are sigmoid function, softmax function, tanh function, and ReLU function. So all these different type of functions are used in different type of applications. So what is a back propagation in a deep learning network? So so what it does is computes the gradient of the loss function with respect to the weights. So once one epoch, that means that if so in one epoch means from input to output. So an x of 1 has traveled from one input from input and it has reached the output. That's the output. So this is called as a one epoch. And once it has reached here, what we will be doing is we will find from this output we will be finding the error function. So what is an error? Error is nothing but the output which we have got and the expected output which we require. So for these inputs x1, x2, x3, we expected an output x. We expected an output y, which is equal to, for example, we expected 6 as an output, but we have got output as 2. So the error is 4. So this error, we need to go back to the hidden layer and we need to change the weights in the in these nodes. So that is what is a back propagation is all about. So computes the gradient of loss function with respect to the weights. Objective of back propagation is to change the weights for neurons in order to bring the error function to minimum. So we need to bring the loss function to a minimum point so that the output is close to what close to the expected output. So that's the reason why we back propagate and we change the weights. Two types of loss functions are used, namely cross entropy, used for error calculation between estimated and predicted probability distribution, and mean squared error. This is used for error calculation between estimated and predicted quantity for regression problems. So one type of deep learning network is a recurrent neural network. So output from previous step is fed as an input to the current step. So this is what is a deep learning hidden layer is. So output from previous step is fed to a current step. So current step. So we have a loop here. So if you see in this diagram, you will be able to find now A is nothing but a node, and we are at a current state, and the input to this is x of t as well as the output from the previous state. So that is what is a yes sir.
I think you are a bit struggling, so I could see with the cough. So
Mm.
probably conclude if it is too long. It may be affecting you. The talk.
No, sir, nothing, sir.
Are you okay?
Yes, sir. Fine, sir.
Okay. Thank you. Take care.
Yes, sir. So that's what a recurrent neural network is all about. So in traditional neural networks, all the inputs and outputs are independent of each other. So that is what a traditional neural network is about. But in cases like when it is required to predict the next word of a sentence. So for example, if we take images application, we don't require a context to that. But in case of a sentence, we need a context to it. So in order to get the context, we need the previous state or the previous word which is there. So for that we do it, we loop it. So the previous words are required, and hence there is a need to remember the previous words as well. So that is what is a recurrent neural network is. And so an RNN remembers each and every information through time. It is useful in time series prediction only because of the features to remember previous input as well. This is called long short-term memory. So what is long short-term memory? Long short-term memory is a type of an RNN. So what it does is it remembers some of the features which are present in the time series prediction. The difference between RNN and long LSTM, that is long short-term memory, is nothing but long short-term memory will remember only the information which which is more important, and it will forget the information which is not required. RNN will remember everything. So that is the difference between RNN and LSTM. Recurrent neural network are even used with convolutional layers to extend the effective pixel neighborhood. So these are some of the issues with the recurrent neural network. So gradient vanishing and exploding problems. Training an RNN is so it becomes a very difficult task to train an RNN because you need to have the data set in such a way that it has all the features, and it has your network should also be in accordance to the data set which you are going to provide. And it cannot process very long sequences if we are using tanh or ReLU as an activation function. We need for some application we need tanh or ReLU. So for those recurrent neural RNN network cannot process very long sequences. So to overcome that, we have a long short-term memory. So in order to overcome the issue of vanishing gradient problem in RNN, LSTMs are used. Uses gating mechanism that controls the memorizing process. Information in LSTM can be stored, written, or read via gates that open and close. So those gates open and close. So we can write something. It's a kind of a memory. So we can write something. It can be stored, and we can read it. So the LSTM cell consists of forget gate. It has a cell state. We have a input gate and an output gate. So these are some of the gates which consist of LSTM. So forget gate, it's responsible for remembering the previous step. We have an input gate, as the name suggests. We have the cell state, so it's the current memory of the LSTM cell. We have an output gate also. This is the structure of an LSTM cell, and how a forget gate looks, how an input gate and output gate looks. So all combined, it will be like this. So we have an input x of t here. We have a h of t minus 1, that's the output from previous cell. And we have first we have a forget gate. So we will using this forget gate, we will forget the information which is not required. Then we have an input gate. From this input gate, we will be storing the information to the cell state. Then we will use the same cell state, and the h of t, that's the output from the previous cell, and we will give it a h of t and c of t. So this is the cell structure of an LSTM. Okay, so that was all about the deep learning part of it. And moving forward, we will be seeing how how deep learning can be used in dynamic analysis. So for to do dynamic analysis, we need an isolated environment. So for that, we create a test bed. So test bed is needed for running the malware files in an isolated environment. So we have an isolated environment. For example, a simple isolated environment is as shown in this figure. We have three systems. So we have one server. We have two host systems. So and this server will be running a dynamic analysis tool like Fox server or Cuckoo server, and the host will be handled by this server. So when you have some malicious or we have some executables, we will run it on these host files. So we will be deploying it here. Then we will get the output from this. Output is nothing but a log file. So from those log files, all the activities or API calls which is being made in by this system on this system will be given back to the server. So for this we use WLS log server as well. So this is combined with the Fox server. You can use Cuckoo server also. So there are different type of dynamic analysis tools which can be used to collect it. So once you do this, we have a collection log is collected, and this log contains all the information about the executable information about the behavior of how the malware has executed. So this is what is the data collection phase in malware detection is. And the image here, if you see image OS is deployed. So what you need to do is whenever you deploy a malware, then image has the Windows image has to be installed fresh image. It should not be a older one. So every time analysis is started, first this image is deployed, and then the executable is run on that. So framework. So how an architecture will look like. So once we get the logs, we will be pre-processing it. We extract some of the semantic informations like the event IDs, or we have some of the network logs from those things. So we will be using a TF-IDF. So TF-IDF is nothing but a term frequency and inverse document frequency. So mostly this is used in search engine. So it's a kind of information extraction. So if you have some document and words using TF-IDF, you will be able to convert those documents into an index base. And when you search for some words, you will be able to get that. So that is what is done here in our training phase. So that information is then given to a anomaly detection model and a classification model. And from that, we will be using these models. We will be finding whether the executable is a ransomware or is a malware or a ransomware or a class of a malware. So log pre-processing. So the first step here is we have already using the testbed, we have collected some of the logs. Then we will do the log parsing. So log parsing is nothing but the logs, like we have event IDs, we have channels, we have some process names and execution threads. So all these are converted using TF-IDF into a vector form. And these vectors are nothing but the representations of the logs. So to convert those things, we use a word2vec library, and using those using word2vec, we convert it into a vectorized form. Then these vectorized form, we convert it into a as an input vectors to the model. So once we get the input as an input, then we use these vectors to train our neural networks. So here we have used bi-directional LSTM CRF network. So LSTM is what we have already seen. So each node has its own forget gate. We have input gate, output gate, gate. So bidirectional LSTM is nothing but it flows in both directions. So it's a variant of LSTM. So it connects two hidden layers of opposite directions to the same output. So by using this, we will be able to learn more number of features which are present in the LSTM in the data set. So once we use this network, the main thing is to get the input in the desired format. Then we will be giving the input data set as an input to bidirectional LSTM CRF network. So from this, we will be getting the output, and in output we will be using softmax X, and for classification we are using argmax. So this is done, and we will once the training is done, as shown here, the testing will be done using a new log and log parser. Then we will test the system, and once it is there, then we can have this model and it gets deployed for the production level deployment. So that was all about the using dynamic analysis for malware detection. And in the future works, we can use some of the more advanced neural networks like sequence to sequence model. We have auto encoders that it can increase the accuracy of the overall model. So that was all about the using deep learning based dynamic analysis for our malware detection. Thank you.
Yeah, thank you, sir, for your valuable insights into this important topic called malware detection and giving us a clear way to do like how to do static and dynamic analysis for malware detection using the deep learning. And once again, thank you, sir. Actually, we had a few questions in the chat box. If you can answer, I will read out one by one, sir.
Yes.
Yeah, so there was a question from Swapna, like on what parameters we can select the best model, either ML or DL for any attack detection. Do we have to experiment with all models or select a random and tune it?
It has to be in a experiment basis itself. If you take a deep learning framework, each and every problem has its own models. So you can test or experiment with the models, and the one of you can go on you're experimenting with like 10 models, and from that you can you can choose one of the model which is best performing and then tune it. Because machine learning or deep learning, it's basically a trial and error method till now itself. So there is no hard and fast rule that you have to use this model only for this kind of work. So you can experiment with the different type of models and select one of the model from that, and then you can tune it to get the best accuracy or good accuracy.
Okay, so another question from Swapna only, like there are many tools for collecting data for identifying attack pattern. Can we rely on one tool or a combination of tools? How strong we should depend on data generated by those tools?
So tool data can be used from these generated from these tools can be used for training. But the thing is it's always better to collect data by your own method. Not relying on other tools. It's better to be to use your own tools and generate your own data. So by that way you will be able to get good accuracy as well.
Okay, so one more last question from the Wembu Selvi. Can you explain how malwares are identical in real-time network traffic?
Okay, in network traffic, it's a bit difficult to find the malwares. So because we have a network packets, from those packets we need to find whether it's malware or not. So I'm also not much knowledgeable on that. So that's what all I know about that. Thank you.
That's all for the questions, sir, for the chat box. And thank you so much for answering all the questions, sir.
Thank you, Dr. Thank you, Dr. Mitran. And Mitran is not only this lecture, he has been coordinating this activity. So I would like to thank him on both things. He was on leave because his health was not well. That's why I was a bit concerned. Thank you. Thank you.
Thank you. Thank you, sir.
Take care.
Thank you, sir. And let me introduce our next speaker and my colleague, Ms. Ishwari Devi. Ms. Ishwari Devi is working in Hardware Security Research Group at SETS. She did her ME in VLSI design. Her research interests include evaluation of side channel analysis using deep learning techniques and development of countermeasures for protecting the crypto algorithms against SCA. She also has experience in bitstream analysis and worked as a part in evolving National Task Force report on cybersec for AI. And warm welcome to Ishwari. Over to you, Ishwari.
Thank you, Nalini. Good afternoon, and I welcome everyone to this session. So this is a session on artificial intelligence and hardware security. So in this session, we'll be focusing on how AI can be used in hardware security. And by end of the session, we will come to know that there is a cat and mouse game in this artificial intelligence and cyber security area. So here is the outline. First, we'll see why hardware security is important, and followed by how AI can be used for for ensuring a trusted hardware. In that, we have four parts which deals with side channel analysis, detecting the hardware trojans, reverse engineering, and how we can also use AI in securing the device when it's being designed physically itself. And next will be on AI on IoT security, followed by digital twin for hardware security. And finally, we'll come to know that AI can be also against hardware security with few examples. So starting with cyber security is protecting the hardware, software, and data from the cyber threats, not only the data or the protecting the system from the malicious software. It is also equally important to protect the hardware. So when AI is used in cyber security, it has ability to detect the hardware, detect the presence of threat, and it has capability to act itself as a defender without the involvement of human beings. So that's why AI is a powerful weapon we can use against cyber threats. And from morning, we had lots of session where we saw how AI can be used in different AI can be used in detecting the malware, spam detections, and followed by we'll also be seeing we have also know that how it can be used in detecting the anomaly detection algorithms, and it is more efficient in detecting the zero-day attacks also. Okay, why hardware security? Why to focus on hardware? So the basic thing is hardware provides a platform for software, executing the software, and also it is used to implement the cryptographic algorithms because of the speed, and it provides the security. Whenever the cryptographic algorithm is implemented in a hardware, we ensure that the algorithm runs in a desired speed based on the clock speeds and other concerns. So when we are using this for the cryptographic application, we should be sure that the hardware is secure. So how we can say that it is secure? The security comes with only with the trusted hardware support plus the trusted software. And the root of trust must be ensured in each and every hardware we use for the cryptographic applications, and even nowadays in IoTs also. So where does this hardware security get affected? What are the attacks? How we get attack in this hardware platform? So major thing which plays a role is the supply chain. So when we are asking a hardware from any other third part, we are getting a hardware, the third party involvement is equally involved. So there is a chance for hardware trojans being inserted by them in the fabrication of chips, or during the transit, or during the installation, anything. So supply chain plays a major role in inserting the hardware trojans inside the hardware. And also equally, we have to see about side channel attacks, fault injection attacks, probing attacks, and what is reverse engineering we'll be seeing. And these fault injection and probing attacks mainly comes under the invasive part, where we need the physical access of the hardware to get connected to its electric signals through wires. So we need a physical interaction in case of probing attacks. Here we won't be going in very detail into it. And here the picture on the right side shows how the hardware impact how the hardware will impact in case cyber attack gets possible. So here the minimum impact is on the application level, whereas the maximum impact is on the hardware platform. So we should ensure that the physical devices, they are equally protected as equal to the software and data we are using. And this is the very recent research result. And this detecting the evasive malware on IoT devices using electromagnetic emanations. And these results were, these findings were presented by the people from Research Institute of Computer Science and Random Systems very recently. What they are saying is, from the IoT device, so as of we know, whenever electric device is being operated, there will be an electromagnetic emanation emitted from that. So what these people have did is they have from the IoT device, they have captured the electromagnetic field emanations, which is called one of the side channel. We'll be seeing what are the other side channels in forthcoming slides. So these people have extracted the EM emanations from the IoT devices, and they have analyzed what are the types of malwares being inserted in it. So they are able to say whether the IoT device is good or whether it is malware affected. So how it is possible, we'll see in our next few slides. Okay, in general, so we can say that cryptanalysis is how far it is just ensuring how far the algorithm is secure. So cyber attack can be classical implementation attacks or other attacks. So in classical attacks, the thing is we'll be focusing on the mathematical things in the cryptographic algorithm, whatever it may be, either the AES or DES. We'll be playing only in the mathematical thing. Whereas implementation attack deals with the hardware which is used to implement the cryptographic algorithm. And the other is social engineering attack, as all we know. And here the focus will be on the implementation attack. So here there will be some process going on in order to gain some information from the physical device in the hardware level. So here we see side channel attack, fault analysis, probing attack, and reverse engineering, which comes under the implementation attack, more related to hardware. Here side channel attack deals with the extracting the secret information from the hardware through the emitted side channels. What are the side channels? We'll see in next slide. Similarly, fault analysis. We'll be inserting a fault as discussed by Professor Chester sir in the morning session, and we'll observe the information from the hardware. Either it can be also a secret key. Fault can be inserted in such a way that the secret is being obtained. And followed by probing attacks, where we need a connection, a real connection to the hardware which is being executing the cryptographic algorithm. And in reverse engineering procedure, will be with the hardware implementation, we'll get to find we'll get to know about the functions and what are all its where it's storing the key, and complete results will be known. So our implementation will be mostly on implementation attack other than probing attacks. And so what are the side channels? So is this really possible to get an information from the side channel? We'll see in coming slides. So whenever an input is given to a electronic device, when it processes the input to give an output, there will be some side channels being emitted. One is timing. So some algorithms may take large time, some may take less time. And some may consume more power, some may consume less power. Equally, EM radiation. It also emits EM radiation. And the temperature, whether if it is a complex algorithm, the device may hit little bit heat. Else the device might be in normal temperature, and the sound. So these are the 5 major side channel informations that we can get from any electronic devices when it is processing an input to produce an output. So these side channel attacks, which comes under implementation attack, is published by Paul Kocher in 1995. And this mainly focuses on the weakness in the physical implementation, that is hardware in which the cryptographic algorithm is implemented. And these side channels, any one of these 5 side channels will be used. We will be storing these side channel informations, and we are able to get the secret or any secret information from the hardware which is having the crypto algorithm running in it. And this is one of the most powerful attack type in hardware security. In active attack, so we can say it as there are 2 major attacks. One is active attack and the other is passive attack. In active attack, the attempts are to alter the system resources which affects their operation. So it will be evident whenever we do a alteration, the output gets affected, the operation gets affected. Whereas in passive attack, the attempts will be made without affecting the system resource. The hardware having the algorithm will run as it is, will give it will produce the intended output. There will be no changes in the output or the operation, but side channel informations will be captured. So here there are three major tampering techniques: non-invasive, semi-invasive, and invasive. In non-invasive technique, the device parameters are not altered. There is no physical contact with the hardware, and it is easy to perform comparatively the invasive and semi-invasive. Whereas in invasive and semi-invasive, we need access to the physical system. In mostly in invasive, as in the picture, we need access to the layers, the internal components, we need access to it. But our focus is on non-invasive. So at sets here we have two measurement setup. One is for power measurement, measuring the power, which is one of the side channel, and the other is EM measurement setup. So we have set up to get the power consumed by the algorithm which is running in the hardware, and also the EM emanations that it emit when an algorithm is running. And so, okay, now we have the information. So for example, if we consider an IoT device as per the recent attack, we have the IoT device, and now we have captured the traces, either power traces or EM traces from the IoT device. Now we have it in our hand. Okay, so now what to do with it? Now, how can we apply any technique to retrieve, to say that the IoT device is good or malware affected? Let's see now. So there is a famous technique called profiled attacks, where we'll be having a similar device to the target device. Here in the profiled attack, we can see two devices. One is with, highlighted with black, and other is the red. The red is the target device and black is the authorized device. So this authorized device, IoT device, is got from an authorized dealer where the root of trust is ensured. And we are going to find out whether this red device, target device, is good or bad. So what we'll be doing is both devices will do a similar operation. And what we'll be doing is we'll capture the information from the profiling device, which is the black one, and we'll have the data set collected, and then we'll compare the data. We'll train the model using this data set, and we'll use this model to test whether the device is good or bad. So here is how we can use DL. We can use DL on performing template attacks. And here the thing is, we have to create a profile using a profile. In the sense, we have to record a large number of PAR or EM traces using many different inputs from the profiling device. So here, this is the profiling device. So here we have to collect large number of power and EM traces from the profiling device, and using this profiling device, we have to train the DL model or ML model, anything. Then after that, when our model is trained, we can record a very small number of traces from the target device, which is from a third-party supplier, and we can apply these attack traces to the trained model, and then we can find whether it is good or infected. So when if it is infected, the model can itself raise an alert that there is behavior which is something different. So this ensures the device ensures root of trust or not, whether we can believe the device got from the third-party supplier. And here is the pictorial view of what I'm trying to explain. So here I'll take the pointer. So here we have the trusted device, and from the trusted device we are getting large number of samples and making the model to learn. And from the device under test, which is closed, here we don't have any control over it internally. Only we can give output and input, and it can process it and it can give output. So we are going to capture these traces also, and we are going to analyze. The result will be whether the hardware can be trusted or not, whether the hardware security is ensured or not. So here the goal is to take advantage of the side channel informations. Any of the five here I have took EM or PAR traces, or we can also take the other five side channels, and we can use those informations to detect whether the model has anomalies or not. So this is the place where AI plays an important role in ensuring the root of trust. So in not without using AI, is this possible? So yes, so there is a thing called template attack, and this template attack in this traditional method of template attack, will be using a statistical calculation and statistical method to find out the to classify the malwares when we are creating a template out of the profiling device. The thing where it comes complex is the template attack becomes difficult to apply when the measurement dimension exceeds the 100 points. So here what I mentioned as 100 points or 100 trace points is we'll be representing the value of the trace in x dimension to some points. It is nothing but the representation. So when it exceeds a very small amount, usually to get more amount of data in a detailed manner, we need trace points above, we'll have trace points about 1 lakh. So where is 1 lakh and 100? So this becomes complex to do when the trace points are more than 100. I mean the traditional template attack. So AI plays an important role here to overcome this complexity, and also it retains the spatial property and the functions. So here the spatial property is here actually the trace is 1D, but this relation between the one point and the next point should be maintained for the model to learn better. So this spatial property will be retained in when we are using the AI model. And also there are many results which show in this reference also we can refer it, and it shows where a convolution neural network can be used to perform this task, this classification task very good than the MLP layer. It's just because this higher number of dimensions and the spatial property. And also the whenever the traces are not in a sync, we have to capture the traces at a particular sync. For example, whenever the operation starts, the traces must get captured, not at the mid of the operation. So these things must be aligned. And even if we are not aligning it manually, the CNN will take, if we are using convolutional neural network, it will take care of the desynchronization and jittering part. And next is the supply chain vulnerability. So, excuse me. So as we discussed earlier, whenever we get an electronic item from the third party, it comes under it passes through various steps like manufacturing. It gets manufactured somewhere. There is a transit, there is an installation, system operation, and there is a thing where we use. So when electronic devices coming through all these steps, we should ensure that there is no attack. I mean, there is no hardware trojan being inserted, or there should be no malicious code being inserted. So there should be an end-to-end supply chain protection in order to prevent the root of trust. And recently, back in 2021 July, they were increasing the supply chain insecurity attacks, and it also results in a great drawback. So what is hardware trojan? We say that the hardware trojan might get inserted when it is being transited. So what is hardware trojan? Okay, before that, what if a smart light or lift in our home gets controlled by anyone else over the internet? It's really a strange thing. And so how it will really become possible? How will it become possible? So one thing is by inserting the hardware trojan. Okay, whenever there is a smart line being exported from some other place, we doesn't know whether the hardware trojan is being inserted or not. It might be one of the reason for controlling the smart light at our home by others over the internet. Okay, so what are these hardware trojans? They are nothing but the malicious modification which are inserted in an electronic device. It may be either a processor or an IC, and it has a capability to change the functionality of the circuit, and it also has a capability to leak the confidential information which is stored in the device. So automatically there is no trust. If I'm getting a hardware to implement a cryptographic algorithm which should secure all other devices or the operation or a communication, what is the use if I have a hardware trojan being inserted in a electronic device? So the trustworthiness is completely gone. We can't guarantee the root of trust in this case. And these hardware trojans, they are not easy to identify, and they are very small compared to the design. And also they are very passive. Only when a particular input or a particular sequence of inputs is given, it gets triggered. And the payload inside the Trojan gets executed only at that point. So it's really a little bit hard to identify whether a device we buy has a hardware Trojan in it or not. Okay, so does this hardware Trojan really matter? Yes, so there is a big hack which was exposed in 2018 uh, by even if we search the big hack in Bloomberg, we can see it. And what the thing happened here is um, there was a motherboard, and it was used in the national intelligence community of US and other top companies like Amazon and Apple, and they were using this motherboard for over a period of time, and they have come to know that they were a very small hardware inside the motherboard which they were using for an important application. And this hardware was very small, and it was inside the inside the jumpers of the motherboard in few boards, and it was between the layers also. Actually, this mother had about 18 to 20 layers, and in few cases this extra hardware was found between the layers. And this was during the this was one of the best example for the supply chain hack which happened recently. And how this hack worked is here. So there was a malicious chip which was very small than the tip of the pencil, as we could see, and it was inserted at the factories which supplied the motherboard by a third party. And this motherboard was manufactured, and then it was made to use by the suppliers in their service. And once this was in action, what it does is it can control the computer system, and it can give access to the attackers, and it can uh, pull out all the information from the other side to the attackers. And this was the great thing which was hardware great example of the hardware security hack. Okay, so now how can we ensure there is a hardware trust? How can we use AI in this area? So before using AI, there is we can if we have a hardware, how can we extract the information? Here the information in the sense, the net list or any memory or DRAM memory or the software or the functionality. How can we extract the functionality and all those stuffs from a hardware? So there is a process called reverse engineering, through which it is an electrical testing or a physical inspection testing, where it will give us the electronic design layout of the or the netlist which is being used in the hardware circuit. And it also using reverse engineering, we can also get out the stored information from the memory. And there is also possibility to get out the functionality and specification used in the hardware for designing. So using this reverse engineering, we can collect more, we can have a set of netlist and set of data, functionality data, which are good. So how can we use AI? So in order to test a device which is good or malicious, before that we need a device which is really trustable. So from the trustable device, we'll be getting the golden data, and we'll be training the model using the golden data, and then we'll be testing the device. We'll see how it is possible. So here is one case where AI can be used for hardware detection. So by the process of reverse engineering from the hardware, we are able to get the gate level netlist. And this from the gate level netlist, we can extract the feature either by using a principal component analysis, which is a famous ML technique for feature extraction. We can extract the feature and we can train the classifier model. So our model is ready now. So here this table shows the data set extracted features, and this data set was from Trust Hub. So here each data set represents, for example, F0, F4. This is a label which represents the Trojan feature, which has F in X, which is nothing but it has X number of inputs from a particular level. So these are all the data sets related to the netlist, which is from Trust Hub. And we can use this data set to train the classifier model. So even here in the feature extraction, there is one work who concentrated on extracting 51 features alone. And out of the 51 features, they extracted 11 features using the random forest classifier, and they used only those 11 features to train the classified model, and even their result showed a best result. And there was other work where they have considered extra 5 features from the base, so 56 in total, and then using the extreme gradient boost classifier, they picked out only 49 features and they have trained the model. So this work showed more accuracy than the previous work. So this is the place where AI plays a major role in hardware Trojan detection and to ensure hardware security. And the other cases, so when a chip is being designed by an authenticated supplier, we have the golden netlist available. So what we'll do is we'll get the fabricated, trusted fabricated piece from the authenticated supplier, and we'll have a golden image of it, and we'll be taking a imaging of the die area for the device under test, which will be compared with the golden gate footprint and the device under test, which will be given to the using the SVM classifier. So SVM classifier will be capable of saying which is good model, which is the good footprint and which is the malicious one. So this is the other application. Previous thing dealt with the netlist, and this thing dealt with the imaging of the die area. So this is also the other possibility where AI can play an important role. So the other thing is in physical inspection of electronics. As we saw in the big hack way back in 2018, there were a very small hardware chip which was inserted between the layers. So there is an possibility to insert between the layers also. So we should check between the layers also. So using the technique called as scanning electron microscopy. So we can use this SEM to get out the SEM images of the each and every physical layer. So we have to scan it out layer by layer. And from this SEM images, we can train the AI model, and we can use the computer vision technique. As we discussed earlier, CNN can be used since this is an image, and we all know that in AI technique, CNN will outperform the classification of images than any other model. So we can use CNN to classify this data. And it is not very easy to get the golden data for this training. It is really a great challenge, and only nowadays we get few golden images, and it is one of the challenging area. Though it is easy to train and detect, but the data set availability is very less. So this is how a scanning electron microscopy images will look like. So this is the layout from which the same images are extracted. So this is how the layout looks like. But here we can see in the red color highlighted thing, we can see there is a change. In this case, there is a change here. compared to the layout, there is a change in the same images. So here also there is a change. So there are change in 4 places. So these changes can be noted and it can be identified using an AI model. And as I said, there are many challenges. One thing is data set, and the other thing is capturing the same images itself. So what if to do if there is a noise at some parts? What if there is a dust? And even while Professor Chester sir was saying, he has zoomed out more to find out where the noise exists. But here it is very evident. So how to deal with this? And this is because of the layering issues, because of not capturing the proper image at each and every layer. So all these challenges has to be taken care of while capturing the same images, and also it is a little bit costly to get it out. And so we can say that there are many possible areas where the hardware trojans can be inserted, or where an malicious modification can be inserted. It starts from design team of the third party supplier, or whether it can be in the CAD tools being used. It can be in the while generating the gate level netlist, or it can be during the physical synthesis. So likewise, there are many places where the trustness can be lost. And here the red color things indicates the untrusted points where there are more possibility to insert a hardware trojan or change the modification of the hardware completely. So we shall see how this can be avoided to a particular extent. And so why don't it be a good idea to use artificial intelligence to ensure physical security during the all process of design flow? And why? Because if a Trojan is being inserted during the design point itself, it will get last up to the end, and there are no possibilities to find it to get it detected. So if we are using AI in the physical design flow itself, at some point it can be detected during the manufacturing process itself. Else we'll be getting even if it is a small chip, we'll be using it to develop support. We will be using it to support the other hardware equipments, which will also be getting infected. So there can be possibility to adapt AI in securing the physical design flow itself, that is during the manufacturing of the hardware itself. And here reinforcement learning can be adapted in ensuring the secure physical design, as it works based on the awards and negative commands. It can learn itself. So it can learn, it can produce a good output than when any other AI model is being used. And as mentioned by Professor Chester sir in the morning, Rowhammer attack. So how actually this Rowhammer attack is made by software. I mean, when this is we have a memory which is made up of number of DRAMs, which are arranged in rows and columns, like as the representation shown here. And when a particular row in a DRAM memory is accessed continuously, so as all we know, DRAM works based on charging it in it works based on the refreshments of charge. It needs refreshing circuit. So if there is an access of a particular row within the refresh period, what will happen is the neighboring cells will get affected. It will drain out its energy, and those data in those cells will get flipped. There is a chance. So by you, and because of this, even the privilege can be changed. Even for example, if this address is responsible for giving user privilege, and if this bit is 1, it might give privilege to one user. If it is 0, it might not give privilege to the user. What if it is changed from 1 to 0 or 0 to 1? It results in a great attack. So even these memory attacks in hardware level, by using the AI technique, it can be protected. I mean, the protection should be brought in the hardware level during the manufacturing itself. And coming to the IoT security, as all we know, IoT is a very small device with a very less memory, and it has very less battery than the hardware elements which we use in the other applications. So while handling these IoT devices, we must be more conscious, and we can't implement a complex AI algorithm in it because it needs strong computational power or high power and very large storage. So in these cases, we can adopt tiny ML, which is which occupies only very less storage, and it can also ensure the trust. I mean, it can also ensure the security in the user's point of view. And one of the reason why this IoT gets affected is, to a network, there are different types of devices being get connected. One may be new, the other may be old, and the operating system in it may vary. So these are the primary tasks for the primary targets for the hackers, as they will use it as a weaker line to attack it. And there is one more application, how AI can be used in digital twin for hardware security. So in general, digital twinners, there will be a virtual twin similar to the hardware we are using. So for example, if there is a car, we'll be having a similar model of the car in a virtual environment. And when this car is on the real time is facing an accident, and this information from the accident, the sensors of the accidental car will go to the digital twin, and then the model gets learned, and it will correct for itself, and such that the next version of the car is not getting affected due to this accident. Some precautionary measures will be there. So adopting the same thing to the hardware security, we can also ensure that there will be hardware security trust being ensured. So here, how can we compare it is, we are going to create a digital twin of the hardware in the virtual world also, and whenever there is an attack, the digital twin in the model, AI model in the digital twin will get updated, and so that the next hardware being produced, manufactured will not get affected by the same attack. So the next part is, can AI be against hardware security? Yes. So as discussed from morning sessions, we saw one of the famous attack is poisoning attack. So as of now, we were using AI for securing the hardware devices. But what if the attacks happen on the AI model which we use to secure the hardware security? So that is an area we have to focus on, and it starting from the data poisoning, algorithm poisoning, and model poisoning. All the security will get affected. So this is an area where we have to get pointed out. And the next thing is side channel attack. So as we discussed earlier, the side channel attack is getting the information from the application being run on an electronic device. So here the attacker has a chance even to infer the secret key which is being run on the cryptographic algorithm in the hardware. So even in this area, the AI can be used to help the attacker to infer the secret key in an easy way. And this is the traditional method how we extract the key from the side channel informations like power or EM. And here the things will go on with the mathematical and the statistical analysis. Whereas if we use AI, we can use it as an easy thing. And this is the pictorial representation of how we should use the how we are going to use the AI in key retrieval. So the main thing is, we'll be capturing the power traces from the device from an unknown key, and we'll be training it we'll be giving it to the trained CNN model, and it will be capable of getting the key. And what if AI is used opposing the physically unclonable puff? So puff is usually used in hardware security and such that it cannot be cloned. and each and every puff has a unique characteristics based on the physical microstructure, and this is because of the manufacturing part, and this is unavoidable. Each and everything will be different. So here we see each and every puff will have different challenge and response. Challenge is nothing but the input and response is the output. So whenever we are using a puff for a particular challenge, we must get a particular response. Only then the device will get authenticated. So this is the area where puff is used in hardware security for authentication. And there is also possibility for AI being used against puff. So there can be the attacker can collect the challenge and response pairs. Only the thing is physically the puff cannot be cloned. Whereas what if the attacker uses the challenge and response and if he clones the puff in an AI model. So this is also one more thing to be concentrated. And so as I said, by end of the talk, we'll come to know that there is a cat and mouse game of security. So we have saw how AI can be used for hardware security and the other thing also. So it can be AI can be against hardware adversaries also, and it can also help the adversary also. So it must be used in a particular way to defend it, and there are also we can also use the countermeasures where AI is being used for adversary. And the other point is the AI security itself can be the target of the attacks. So as said, the data poisoning attack and fault injection attack, those all comes in this point. And so these are the references used. And thank you. So as we mentioned in the morning, we have a task force report on cybersecurity for AI in the link provided below, or you can also see it in the announcement section in our website. We'll also post the link in the chat box. Thank you. If there are questions, it can be posted in the chat box.
Yeah, thank you so much, Ishwari, for giving elaborated talk towards hardware security and also giving us idea about like how can we apply AI for hardware Trojan detection. And I think it will give some key points for the people who are doing research in this specific area. Thank you so much once again, Ishwari.
Thank you.
And we will see.
From my side also, I would like to thank you for excellent coverage. I think you covered everything that's possible in hardware security, especially using AI. Thank you. It's a wonderful presentation. Thanks.
Thank you, sir. Thank you, sir.
Actually, as of now, there are no questions in the chat box. So if anyone had any questions, you can post it in the chat box. Yeah, it gives me immense pleasure to introduce our next speaker, Ms. Samita. So Ms. Samita is currently working as a scientist at SETS. She did her BTech in Information and Communication Technology from Shastra University, Tanjavur. She is currently working in the area of post-quantum cryptography. In cybersecurity, her areas of interest include cryptology, artificial intelligence, and VAPT. She is a SETS certified ethical hacker and was a topper of the SETS certification on Advanced Network Security (SCANS) course. And we welcome you, Samita, and over to you.
Thank you, Nalini. Good evening to everyone. Today we are going to discuss about how deep learning can be used for feature extraction in network intrusion detection. So first, the overview of the talk is going to be, we'll discuss what are intrusion detection systems and how exactly feature extraction. We have earlier learned about feature extraction in deep learning, how it can be used for intrusion detection system. How do we efficiently detect attacks, cyber attacks in the real time? So we're going to study about that. And then we are also seeing about a special class of neural networks called the autoencoders and sparse autoencoders. And we have earlier said that we are going to see how do we do feature extraction using deep learning, and that too for an intrusion detection system. So we'll discuss what is the data set used and what are the steps in detail. The talk is entirely based on a research paper by Bingo Yen et al. It was published in the year 2018 in IEEE Access. Let's start with intrusion detection system. Let's understand the intrusion detection system. So whenever a cyber attack is happening in a network, if you're in an organization or a college, so when a cyber attack is happening to you, be it any kind of cyber attack, let's consider it as a DOS, any unauthorized access to a system will be detected by this intrusion detection system if it is installed in your network. So intrusion detection system, as the name says, it is used for identifying or detecting any cyber attacks that is happening in your network. So if you ask me, is this technology new? This technology is not relatively new. It has been in the past 20 years. So how do we? So what is this IDS capable of? It does not only capture the attacks like DOS, which is happening outside the network. It is also capable of detecting insider attacks. So we've understood that intrusion detection system is primarily used for detecting any cyber attack that is happening in your network. And then since we are talking about IDS, there is other device which is similar to an IDS, that is intrusion prevention system. But what we are going to discuss today is intrusion detection system. So let's understand the difference between IDS and an IPS. If you look at the diagram on the left talks about intrusion detection system, and the diagram on the right shows about intrusion prevention system. If you look at the diagram carefully, whenever an attack is happening, it is led into the network. This corporate LAN tells you the internal network. So whenever an attack is happening, it is led into the network, and whatever is being sent, whatever traffic, network traffic, we usually talk in terms of network traffic and network packets. So whatever packet is coming, it is sent into the internal network, and a copy of it is being sent into the IDS. So you can think of IDS as a passive device. But if you consider in the case of intrusion prevention system, this IPS sits between the firewall and the switch. So whatever network traffic or network packet, it has to go through the IPS to enter the internal network. So in case of an IDS, it is a passive device. In case of an IPS, it is an active device. To understand more, you can think of IDS as a security camera, CCTV camera installed. So if there is any attack happening, the CCTV camera will record it, but it will not prevent the attack from happening. But if you consider IPS is like a security checkpoint. So when you're entering a unauthorized organization, there is a security checkpoint. So if you are an unauthorized person, the security will not let you in. So that is the difference between an IDS and an IPS. But although this IDS is passive, if there is any attack detected, it will alert the administrator. And so if you ask me if we should install an IDS or an IPS to detect cyber attacks, IDS is like very efficient because only a copy of it is sent, so it can alert. But since this IPS is slow, because every time when an attack happens, every time when a traffic, not only attack, even if it is a normal traffic, it has to go through IPS. So it takes a lot of time to process. What is the goal of IDS? The goal of IDS is to detect attacks, as we seen earlier, which was not detected by other mechanisms which were in place, like filtering, packet filtering routers, firewalls. So if an attack is not detected by a firewall or a packet filtering routers, it can be detected by an IDS. So also with the IDS, you can know in depth about the attack, what has happened. What are the two types of IDS which is available is the network-based intrusion detection system, and then we have the host-based intrusion detection system. What is a network-based intrusion detection system is, earlier example we saw of two diagrams, that is network intrusion detection system, because IDS is placed as a common device for the whole network. So instead, there are other IDS also called as the host-based intrusion detection system, wherein in every single computer in a network, for example, you're sitting in your college and in every system, a host-based IDS can be installed. So what is the difference? So NIDS is more efficient because it has a knowledge of all the traffic or all the packet that is entering the network. But HIDS has only access to that particular system. So in a way, network IDS covers a large ground of attacks. It can detect a large ground of, it has more control over the network than a HIDS. What are the different, okay, we have been talking that IDS can do this, IDS can detect attacks. How does it do? So how does it detect an attack? It is usually, there are two types of detection. There are three types of detection technique being used in an IDS. One is the signature based IDS, and then we have the anomaly based IDS. Third is in hybrid detection. Let's look into what is the signature based IDS and anomaly based IDS. Our whatever ideas that we develop using artificial intelligence technique, it comes under the anomaly based ideas. Signature based ideas in the sense, so whenever a network traffic comes, so somebody is trying to access a data from the internal network, the packet will be predetermined, the packet will be analyzed. So there has been a lot of network traffic. It will be analyzed to identify a particular pattern. So any network attack which is happening, for example, a DDoS flood is happening. So it will be analyzed and a corresponding signature, a pattern will be derived from it, known as the signature. So this to relate this, you can think of antivirus. If you download an antivirus, what happens is that how an antivirus detects a virus is that it has a set of signatures. So that is why people recommend that you always update your antivirus. So whenever a new attack comes, corresponding signature for the corresponding signature for the newly found attack will be sent as a patch to the antivirus. When an attack is happening to your system, what it happens is the attack is matched with a pattern which is already present in the antivirus. If the pattern matches, your antivirus in the system tells you that it is a cyber attack or it is a malicious activity which is happening. And signature based ideas is like when you have a traffic, you analyze it, you identify certain patterns from it, and you keep it as signature. So whenever the same attack happens again, you match it with the signature. If the signature matches, you say that it is a cyber attack. And it is highly accurate. It has very less false positive rate because for the corresponding attack, you have the signature. And then we talked about, we said that there are two major classification. One is the signature based detection, other is the anomaly based detection. What was this need to go for anomaly based detection? We'll see. So if you look at the advantages, it is highly effective because a cyber attack, if a DDoS flood is happening, it can match the signature and it can tell you on spot that it is a DDoS attack. It has very less false positive rate. But if you look at the disadvantages, the signature is like for zero-day attacks, you cannot develop signatures. So only after the attack happened, you come to know that it is an attack, and signatures has to be developed later on. So for many attacks, for any zero-day attack, you will not have signatures. In that case, you will prefer an anomaly-based IDS. So and then these signature-based IDS can easily be bypassed. So if you have a attack, you have derived a signature. If the attack pattern is slightly modified, the signature pattern would not match. So in that case, it can easily bypass a signature-based IDS. So the motivation for go to anomaly-based IDS is the disadvantages in the signature-based IDS. But by all means, signature-based IDS has a lower false positive rate. And then we'll discuss about the anomaly-based IDS. Anomaly-based IDS is the every machine learning or deep learning based IDS comes under this anomaly based IDS, wherein every network traffic is put into a deep learning model or a machine learning model, and the output will be like whether it is a normal traffic or an attack. This classification is done by a machine learning model, then it is called a anomaly based IDS. And then what is the disadvantage of this anomaly based IDS? If the model is not trained well, if the model has very less data to be trained on, then it could give you high false positive. So even malicious, even if it is normal traffic, if the model is not been trained for it, it will think that it is a new activity happening and it will classify it as an attack. So the only disadvantage of anomaly based IDS is it has a high false positive rate. And then we now understood on detail how an IDS works. So let's understand what is feature extraction and how do when we talk of feature extraction, the main thing that comes to our mind is PCA, machine learning algorithms that usually fall under this feature extraction category. And then how do you do this feature extraction using deep learning? Let's discuss into that. What is a feature? Since we have discussed from the morning features, you can think of features as if you have a data set. you can think of the columns as a feature. Features are already, features can also be pronounced as attribute. You can use the terms alternatively, and it tells you features decides, not all features correspond to your decision. So whenever there is a real data set which is collected, it can have a lot of noisy data, it can have a lot of irrelevant data and very little of useful data. So even if you think of IDS, if you want to collect network traffic in your system, in your network, you're trying to capture, you're trying to collect data. Most of the time it will be normal traffic, right? So it is noisy data for us because we are trying to identify malicious traffic, but you'll not get this malicious traffic on a daily basis. And then what if you train your model without removing the needed features? What if you train with the noisy and irrelevant data? What can happen is that the prediction obtained from such a model will not be accurate, and it will also slow down if you have a huge amount of data, because this data already contains noisy data and irrelevant data. The process might take long to train, and then it can cause overfitting. And overfitting in the sense, we know that overfitting is a model is being trained on the data set, but when it is put to testing or when it is deployed in the actual environment, the model doesn't perform well. So if noisy and irrelevant data are there, it can cause overfitting. And then how do we do this using deep learning? If you look into deep learning, I've broadly classified into supervised learning and unsupervised learning. Supervised learning, feed-forward neural networks, convolutional neural networks, and recurrent neural networks we have under supervised learning. What do we mean by that? All the classification tasks are primarily done. These are the neural networks which are primarily used for doing classification. There are other subclass of neural networks called autoencoders and restricted Boltzmann machine. These are primarily used for carrying out unsupervised learning. Unsupervised learning tasks in the sense it can be used for doing a feature extraction. So how do we combine both? There is a category of neural network called deep belief network, wherein initially when you look at this autoencoder and RBM, we call it as it is primarily used for feature extraction. So what you can do is, if there is in your data set, if you have like thousands of columns, and not all 1,000 columns would create an impact on the selecting and arriving at a decision. So what you can do is, you can put all the 1,000 columns into an autoencoder or a restricted Boltzmann machine, and you can identify only certain columns which has actual impact on the output on the decision. And then this output can be given to any of the supervised learning classifiers. So that is a deep belief network. Deep belief network in the sense, you have an autoencoder and an RBM in the unsupervised learning phase. Then in the supervised learning phase, it will actually classify. So we saw that autoencoders can be used for doing this feature extraction. How does an autoencoder does this feature extraction? Let's look at that. Autoencoders are very much similar to a feed-forward neural network. If you look at the diagram, this is how a simple autoencoder looks like. The X-axis, the neurons in the red is the input phase or the input layer, and the neurons in the green are the output layer, and the neurons in the blue color are the hidden layer. So what happens in a normal neural network is that you provide all your inputs to the input layer, and then the model tries to predict an output, which is usually, and then you compute a loss function using either a mean squared error method or a categorical cross entropy. But in this case, what happens is that instead of classifying into any class, the model tries to reconstruct the initial input. So in order to understand this better, you can think of file compression. For example, if you have a 15 MB of file and you're trying to compress it into 600 KB. And then from this 600 KB, you're trying to reconstruct 15 MB. If you're able to reconstruct 15 MB of data, if you're able to capture whatever is there in the 15 MB into a 600 KB file, it means that whenever you want a 15 MB file, you can, instead of that large sized file, you can use the 600 KB file. So that is how an autoencoder works. And then dimension, what do we mean? We said that there are two phases.
there is an encoding phase and then there is a decoding phase. In the encoding phase, what happens is that you give all your inputs in the input layer. So we usually, the number of neurons, how do you decide on the number of neurons to the input layer? You decide on based on the number of features or number of columns you have in the dataset. For example, if I have like 5 columns in a dataset, I give each data to the input layer, and then I don't want, I feel like this 5 columns is large. I want it to be compressed. So I give it to the input layer and I compute the neurons in the hidden layer. Now 5 neurons has been compressed to 4 neurons. So what does it mean? If you are able to reconstruct all the 5 which was provided as input from this 4, it means that instead of using the input xi, you can use h. So the output layer is not actually xi cap, but in turn the hidden layer h. So encoding phase is nothing but from xi you try to compress into h, and decoding phase is nothing but you decompress from h to xi cap. So the loss function computation will be like you try to minimize the loss between xi cap and xi. If you look at the usual feed-forward neural network, it would have been actual output minus the predicted output, the whole square. So since it is a reconstruction-based neural network, here the loss function will be xi cap minus xij. Both are inputs. If you're able to successfully reconstruct, you can use the hidden layer as output. And then there are different types of autoencoders. One is a undercomplete autoencoder and the other is an overcomplete autoencoder. What do we mean by an undercomplete autoencoder is that I say the dimension of h is less than dimension of xi. We call that as an undercomplete autoencoder. What do we mean by dimension? Dimension is nothing but number of neurons in the dimension of h is number of neurons in the h layer, and dimension of xi is number of neurons in the input layer. So if it is this way, it is called as an undercomplete autoencoder. So if you're able to successfully capture whatever is there in that 15 MB of file into a 600 KB file, I said that you can use the 600 KB file instead of the 15 MB file. What if your autoencoder, instead of compressing, learning everything and providing an overview into this H, what if it directly copies? Instead of from 5 neurons to this 4 neurons, what if it copies the first neuron to the first neuron, second to the second, third to the third, and fourth to the fourth? It is not actually exactly encoding it, it's just copying it. So in order to prevent this, there is a technique called as this in other terms is overfitting, right? So if we face overfitting, what do we do is regularize. So you can think of sparse autoencoder as a regularization of the autoencoder. So let's look at sparse autoencoder. What does sparse autoencoder do? What was the motivation for going sparse autoencoder is that there are some times when instead of compressing, instead of providing, learning everything and providing a compressed version, the model could only capture very less irrelevant information. To avoid this overfitting, we go for sparse autoencoders. How do we achieve sparse autoencoding is that, how do we prevent this overfitting happening is that we enable only less number of neurons. We make instead of copying all the 4 from the first 4 to the second 4 in the next layer, what we do is that we enable only certain neurons and then we keep the remaining neurons inactive for a longer time. So this ensures that the model actually learns instead of directly copying from the input layer to the hidden layer. So how do you achieve this sparse autoencoding in a coding point of view? What you do is you activate a neuron whenever we know that we know about activation functions, right? So in the case of in the case of a neural network, in the output layer, most of the times we'll use softmax activation function. But in between, in all the hidden layers, we use a sigmoid or a ReLU activation function. So if you use a sigmoid activation function, it will have values between 0 and 1. So what are we talking about? Our focus is to to keep many of the neurons inactive for a large number of time. So how do you achieve that? You activate a neuron when its output is close to 1. You do not activate a neuron if its output is close to 0. So what is your motive here? You have to keep a neuron inactive for a longer time, most of the times. So when we think of most of the times, the solution that should hit our mind is the average activation function. So what you want to ensure is the average activation function is close to 0 most of the times. Most of the times is significant to average. So here rho L is the average activation function. L defines the neuron. For example, if it is rho 1, this is done in the H layer. So rho 1 denotes the first neuron in the H layer. So what you do, M is the number of rows in your database. You compute the average activation function by you give all the examples, you compute the activation function, you take the average of it. It is easier said. There is a sparsity parameter. This is a hyper parameter. This has to be decided by the developer. So whenever this rho L cap is equal to rho, this rho we want to keep it close to 0 because we want our motive is to keep a neuron inactive for most of the times. So you keep this rho L is close to rho. So this sparsity parameter, which is close to 0, most of the times it is 0.02 or 0.05. If you do this rho L cap, you have to ensure that this rho L cap is nothing but average activation function. You have to set this average activation function is close to the sparsity parameter rho. So how do you ensure this while coding? You can use, there are many ways of doing it. One way of doing it is using the KL divergence. So how do you enforce that rho L is equal to rho? This you compute a loss, you modify the loss function of the autoencoder. This L dash theta is nothing but the normal loss function which is used during the backpropagation network. So you add an omega of theta. This omega of theta is for computing this, is for establishing that rho L is equal to rho. This is nothing but this omega of theta is nothing but KL divergence. So you add this omega of theta to the usual L dash of theta. Now, if you train the model, most of the neurons will not be active. So instead of directly copying from the previous layer to the next layer, the model will actually learn the features. So this is how a model can extract meaningful features instead of relying on the entire feature table. Next, let's look at how we can use this autoencoders for feature extraction for ideas. What is the data set which has been used? We'll discuss on the data set first. Let's explore the data set. Most commonly used data sets for intrusion detections are KDD99 data set and the NSL KDD. So what we'll be discussing is the NSL KDD data set because in the Yon et al. Paper, they've carried out this feature extraction for IDS using deep learning. With the help of this, they've used this NSL KDD data set. What is this NSL KDD dataset? It is a cleaned up, improvised version of the KDD19 dataset. KDD99 dataset is nothing but in the year of 1999, a community of developers came up with an idea that there needs to be data collection, there needs to be public data available for identifying cyber attacks using data mining techniques. So knowledge discovery and data mining tools competition was conducted in 1999 to collect a large number of traffic records. So this NSL KDD is our data set now. So if you analyze the data set, there are around 43 features in the data set, and there are this number of training samples and 22,000 testing samples with 43 features. So if you have to analyze this 43 features in detail, 41 features refer to the traffic input, and then the remaining 2 features refer to the output. So 41 features are the traffic input and the 2 output labels being what is the category of attack and the score for the attack. We said that a traffic, whenever a network traffic comes, it is being classified into whether it is an attack or whether it is a normal traffic. So if it is an attack, we need to specify which category of attack it belongs to. So in this NSL KDD, there are 4 classes of attacks. So totally we have like 5 classes of attack, 5 classes in total, 4 classes of attack and 1 for the normal traffic. So what are the 4 classes of attack? Is it DOS attack? DOS attack, as we all know, so a large number of traffic hits the system. So that traffic is being captured and it is provided under the DOS attack. So whenever a large number of packets come in, it will be come in and it is not making any connection, but it is disrupting the service. It will be put under DOS attack. And then there is another category of classes called as the probe or surveillance attack. All the scanning or whenever a person scans your network or whenever a person scans the ports, now the open ports, it will be recorded under the probe or surveillance attack. And then there is the other category of attack known as the user to root attack. User to root attack is nothing but a person who he has logged in as a normal user, but he is trying to get root privileges. So such category of attacks will be recorded under the user to root attacks. If you look at the remote to local attacks, if you're working on a remote machine and you're trying to gain local access to it. So these are the four major category of attacks which is provided in the NSL-KDD dataset. If you have to classify it further, if you want your data traffic to be classified into some more subclasses, these are the subclasses it covers. Under the DOS attack, we have the Neptune attack. Neptune attack is nothing but a SYN-FLOOD attack. And then we have Smurf attack. And then in probe attack, as we discussed earlier, it includes Nmap scan. So instead of directly, whenever a network traffic comes, instead of classifying it into a normal and malicious, we classified into any one of the following four classes under normal traffic. So even if you want your model to precisely denote which category of attack it belongs to, we can design the output layer based on these subclasses. If you, there is an important point that we have to note that in this NSL-KDD dataset, although it has this much of nearly 1 lakh training samples and 22,000 test samples, it has very less number of data records that relate to this user to root attack and remote to local attack. And how does this impact? Let's see later. Let's analyze the input features. We now saw that there are two classes of output features. What are the class of input features? We have, if we have to classify the input features, we saw that there are 41 features and then these 41 input features. The input features are broadly classified into intrinsic. Intrinsic is that whenever a network packet comes, if you derive whatever information which is provided in the header of the packet, it comes under the intrinsic features. So when you analyze the packet, when you analyze the payload of the packet, it comes under the content. So out of the 41 input features, the first 9 input feature correspond to the category of intrinsic and the next 12 correspond to the content. And then time-based. Time-based is nothing but, time-based features is nothing but it represents a count. In a 2-second window, how many connections has been made. This corresponds to the time-based features. If it is a host-based feature, it instead of a 2-second window, it is a longer window. This is also a count. So this is the 41 features which is available in the NSL-KDD dataset. Let's see how we can use this data set which has 41 features and we'll put this 41 features into our autoencoder. Let's see how many, what is the meaningful information it learned from the whole of the 41 features and how it was able to aid the classification better. The first step before providing it to the autoencoder is the data preprocessing. Since we saw that it had 41 features, there is a feature named number of outbound commands. This feature was all 0. So in the preprocessing phase, this column was entirely removed. So 41 features got reduced to 40 features. And then this NSL-KDD dataset was a combination of numerical record as well as categorical records. Numerical features can be directly provided to the autoencoder, whereas in the case of categorical data, it has to be put through one-hot encoding, wherein for every alphabetic or categorical data, it is converted into a corresponding number. And then in order to compare features, we need a normalization in place. And the normalization which has been used here is the maximum minimum normalization. There are other methods of normalization also available. We can also look at the Z-score normalization. Now what we have done till now is we have taken the 41 features, we have removed one column and made it to 40 features. We have converted all the categorical data into numerical data and we have done normalization. Now we have provided this input to our autoencoder and we have obtained a less number of features, and we have to understand that this is not feature selection and it is feature extraction. What does it mean? If you give 41 features, for example, input port, output port, source address, destination address, etc. It will the autoencoder will not select a particular feature which has high importance. It is only a latent representation. So the output of an autoencoder will not be a selected features. For example, if you have 41 features in the beginning, it will not tell you 10 features at the end, which has been selected from this 41 features. It is only an abstract or a latent representation which has been learned by this autoencoder. So if you compare let's compare the performance of this autoencoder. The performance chart which has been given here, the performance table which is given here is not the autoencoder output alone. The autoencoder has been used as a combination with an SVM, and then we predict its classification. So if you have a number of layers as 6 layers in the 6 hidden layers in the autoencoder, it was able to achieve an accuracy of 99.32%, and the time it takes to train is 23 seconds. And then we have a category of detection rate and a false alarm rate. So if you talk about evaluation parameters, there are a series of evaluation parameters. Like we have accuracy, we have false error rate, and then we have detection rate, we have precision recall. So we have to look at, so a person who is doing a machine learning or a deep learning analysis shouldn't be biased towards only looking at accuracy, because accuracy is important, but more than that, in our case in IDS, false alarm rate is more, we give priority to false alarm rate. So you have to select an evaluation parameter, evaluation metric that is more suitable to you instead of only relying on the accuracy. So if you see, a maximum performance is obtained when you have 4 layers, 4 hidden layers, and if you have the number of neurons decline in the order of in this order, decreasing order, you were able to achieve good accuracy and lower false alarm rate. So in this, if you look at the table, you were able to achieve a lower false alarm rate of 0.131 and 0.136. So I'm going to go with the one that gave us 0.131 as false alarm rate. So it will be, so if you have an autoencoder with 180, 50, 30 neurons in the hidden layers, using this NSL KDD dataset, it has provided us with this lower false alarm rate. So how does it, we need to know if it has improved the efficiency. So instead of directly using an SVM to classify, and now using an sparse autoencoder, followed before using an SVM, we have to compare if the performance has been increased. If you look at it, instead of directly using an SVM to classify whether it is a normal traffic or a benign traffic, in this SSAE plus SVM case, what we have done is we have put an autoencoder. We have learned features which are more which have more impact on the output, and then we have followed it with an SVM. So if you compare its performance, this SSAE plus SVM seems to have a high accuracy and a lower false alarm rate. And if you ask 99.02 and 99.35, it doesn't seem to have much of a difference in terms of accuracy. But if you look at the training time has significantly reduced. So instead of directly classifying, if you directly classify based on the data set, it has taken 73 seconds. But if you use a SSAE followed by a SVM, it has taken less training time. So we can make a statement that if you use an unsupervised pre-training before classification, it gives you lesser training time. Now we saw how long it takes to classify, and then how much percent it has correctly classified. So whenever a traffic comes, it has to classify it as a normal traffic, or it is a DOS, or it is a probe attack, or it is an R2L or an U2R attack. So how many percentage of the times the model was able to achieve perfectly? The proposed method here is the SSAE plus SVM. We have chosen this because this has the lower training time and lower testing time. So that comes under the proposed method. If you look at it, instead of if you use an LSTM to carry out an IDS to classify an attack, it was able to 99.5% of the time it was able to classify a normal traffic, and then 30.40% only it was able to classify R2L attack. If you look at the proposed method, which was SSAE plus SVM, it was able to classify 83.43% of the times and U2R as 67.94. It is significantly lesser percentage of the times it is identifying the attack than the normal traffic. So whenever a normal traffic comes, it is able to say 99% of the time it is able to correctly detect it as normal traffic. So but whenever R2L comes, only 83% of the times it works fine. So why was this difference? Why is this huge difference? Let's look into that detail. There is less, we already saw that we have lesser number of data set, we have lesser number of records in the data set for this R2L and U2R. This is because of the class imbalance problem that usually exists in the data set of this intrusion detection system data sets. As we look at it, this KDD19 data set is still in use, but this data set came in 1999. It might not cover a huge range of attack, or it might not contain huge pattern corresponding to the current age. So it has very less data set for this R2L and U2R category, obviously due to the class imbalance. And then hence it could be one of the reason for classifying it with a lesser percentage. And then there is a chance that the model, the autoencoder or the model which we followed it up would have thought that since it is a lower majority, it would have thought that it is an outlier. So in that case also it would have been missed. So these are all the causes for the lower percentage of detection. So I provided the references. Thank you. If you have any queries, we can take it up.
Thank you so much, Samita, for your enlightening talk. Extraction for the network intrusion detection using deep learning and explaining with some examples. And once again, thank you, Samita.
Thank you, Nalini.
And if you had any questions, you can post it in the chat box. Actually, we had some questions in the chat box. I will read out one by one. Narendra asking about signature-based IDs implemented the switch of fiber.
So this IDS can be, there are advanced devices available called the Unified Threat Management Device. It comprises IDS, switch and firewall. So nowadays you're able to get UTMs which have this, which come up with, which has this AI-based technologies to detect intrusion. So it is not at switch or firewall level. It is above that. It is above. It is at the UTM level.
Another question from Meghna Murthy. How autoencoders select features if the dataset doesn't have labels?
So as we saw, autoencoders doesn't do feature selection. What it does is feature extraction. It doesn't tell you if it is like 41 features are present. It doesn't select first 10 features which has, or the any 10 features which has most impact on it. It learns from the 41 features and it gives you whatever it has learned in a latent level. So you can't compare feature selection with feature extraction.
So another question from Natarajan sir, it would be great if you could differentiate encoder or decoder and transformation or inverse transformation.
Differentiate encoder, decoder,
and transformation and inverse transformation.
Encoder, you can to address this, you can think of an example. For example, you have a file which is like large. For example, you have a 2 GB movie. So what happens is that you this in this encoding phase, what I'll do is I'll take this 2 GB movie and I'll compress it to a 2-minute trailer. For example, 2-hour movie, I'm compressing it into a 2-minute trailer. This process is called encoding. And then this 2-minute trailer, if I'm able to, from this 2-minute trailer, if I'm able to get this 2-hour movie, then it means that whatever is being said in the 2-hour movie, I've captured it well. So instead of circulating this 2-hour movie, I can circulate a trailer. So that is what the difference between encoder and decoder. In a way, you can, since abstractly it is encoding and decoding, but if you have to look at the programming level, you can think of the encoder as a transformation and the decoding phase as the inverse transformation.
Okay. Another question from Prashant. Are there any recent datasets available or efforts by any agency to compile them? Are there any recent data sets available or efforts by any agency to compile?
There is a Kyoto dataset which came in 2009, I believe. What I know is these datasets cover a large category of attacks. Because there could be many, you can collect. There was one question by Ms. Swapnil whether you can use tools for collecting data. But if you collect data, there could again be this class imbalance problem because you would be collecting normal traffic, because on a daily basis you will have most of the normal traffic and not much traffic for the attack category. So it is better to use publicly available dataset. And to address this question, there are recent datasets, I believe, but there we have to identify standard datasets to avoid this class imbalance.
And another question from Vengu Selvi: how anomalies can be detected in encrypted traffic without decryption? Is NSL KDD addressing encrypted traffic?
It is not this encrypted traffic, whatever data set which is available, it is after put into a packet analyzer. So whatever this NSL KDD data set has, it is encrypted traffic. It is put into a packet analyzer. After that, the decrypted traffic is populated as data set. So whatever is available in the NSL KDD data set is a decrypted version of the traffic.
And one more question from Ravi: how frequently NSL KDD datasets are updated?
I don't think there is continuous efforts to update this NSL KDD dataset. There are new datasets. The same community is not updating the NSL KDD dataset because there are new datasets which have come, which is more technologically advanced, which addresses more category of attack than the NSL KDD. So many people prefer the standardized latest datasets.
Last question from Kader: how many latent variables in autoencoder?
So if you ask how many latent variables in an autoencoder, it depends on the number of neurons you have in the hidden layer. If you have four neurons in the hidden layer and input as 100 neurons in the input layer, from 100 features, you have reduced it to 4 features. So the number of latent variable depends on the number of neurons in the hidden layer.
So actually, almost all the questions are covered. And if any balance is there, she will answer in the chat box. And one small announcement, actually we had put a link for feedback form. So you can find it from the chat box. So please kindly submit the feedback form as early as possible. So you can find that link in the chat box. And may I now request our executive director to give the out of time.
Yeah, thanks to everyone, and it's a wonderful journey right from the morning to evening. Normally, physical workshops and all are sitting through one day with some tea breaks and all would be good. But webinar over a full long day, it's a bit difficult. But I could see that the participants have shown immense interest and they have been listening to and interacting with the speakers. So I feel quite elated to see this kind of a webinar and the participants especially. And nowhere the speakers are maintaining a very good, the focus on the subject that they were assigned to, and they were able to deliver good talks over a period of time from academics and R&D labs. And it's a wonderful experience. And I thank everyone. Starting from the keynote address given by Dr. Anand Mohan, sir, and the speakers, Professor Chester, IIT Madras, Professor Richa Singh, IIT Jodhpur, Sri Ramesh Naidu from CDAC, Mr. Swati Mitran, Ishwari Devi, and Samyukta from our labs, our colleagues. So everyone, they have done a wonderful thing, and more or less they maintained time too, and we just exceeded 20 minutes about completing all the tasks. Thanks to every speaker for this, and also the coordinators, Mitran, for taking the technical lead, and in spite of his health problems, he continued and also managed to deliver a talk. And Dr. Rao, who was instrumental in getting the participants and doing many other administrative things, with the guidance of Dr. Lakshmanan, who is our Chief Administrative Accounts Officer. They were all part of it. And I'm happy to see the very focused comparing by Forum and Nalini in both this, and thanks to them as well. And thanks to Vaishnavi for ably managing the Microsoft Teams, and of course there are minor issues, but there she managed timely. And thanks to everyone, and especially I would like to fail to, if I don't thank our PSS office, which has supported our AI and cybersecurity activity, as they have already informed to you a very detailed task force report. Those who are interested, what are the important areas? It's completely came in 100 pages plus document, and it's available on our website or on our PSS website. They are supported, and it has been guiding factor to all of us to work on different areas. And we keenly look forward to the continued support of Office of PSA, especially Dr. Preeti and Dr. Arun Bharadwaj, who are instrumental in helping us in this. And once again, thanks to participants for your, the excellent, the maintaining the rapport with the thing. And I am sure you all continue to, interact with the speakers or sets for anything, and keep watching our website, because we have the habit of doing regularly the webinars, workshops, and training programs. And I would also have a thank Dr. Prem Lakshman Das for his, the giving the preamble or overview of the workshop. And also he is the leading the AI activity in our center with his cryptology background, and it's definitely very interesting webinar. And thanks to everyone. If I missed someone, it's no intention to miss, but I'm very happy to, in fact, probably recent times I have attended a full day webinar from my side also, and I could see the keen interest with which the speakers explained with the background and experience they have and expertise they have. Thanks once again. Thanks to everyone.
I would like to thank our Executive Director, Dr. Chandrababu sir, for coordinating and helping us to making this event grand successful. Once again, thank you so much, sir.
Welcome, madam.
We will end up the section. Thank you all the participants for your patience listening and making this event grand successful.
Formally, we are closing the event. Thank you all.